connects with what for what reason. And with local log, you have a scope which you can see and identify what is protected what. And the remaining users are mostly used to assert passive view variables or hardware registers, at which point it's mostly totally fine to have it as is. So with all this, we ended up with log ordering. There is a document in the kernel with So looking at PrintK does mostly three things. The first thing is it looks at the format string and puts it then in the ring buffer. That's like the first step. And once that happened, it goes via all the console drivers and invokes the PrintK routine. So here we could think, do we go for a ROS bin lock there, or do we do something else? If you look at the times that the UART may spend at 11,000 baud rate, then we get roughly 86 microseconds for a single character to get through. And if we intend to print 20 characters, we end up with 1.5 millisecond where the interrupts are disabled. And from RT point of view, this is way too much. We have use cases where we try to get below 100 microseconds. So this is not working. You could argue that we could disable printing for the normal things and go only for the warnings and errors to ensure they're always printed, and then go for the ROS bin lock T. However, if we make the change, everyone is using that. Even if you don't do console at all, you only use your UART for Bluetooth communication, for instance, then this will also disable interrupts for the Bluetooth communication. So this isn't helping at all. So for that reason, for RT point of view, we need to have a way to avoid disabling interrupts while things are printed on the console. And in the end, for the 6.0 merge window, I suggested to exactly that, to avoid printing. And this wasn't liked very much. So now we basically, step back again, and now we're actually waiting for PrintK to be somehow tackled, that we can print as well as from NMI or non-interruptible context, as well for everyone else, without getting into high latencies. Long latencies. So this is like one example how to get there. Like, we cannot schedule for one reason or another, and then we may have a list with items that we work on. Like one example was the PrintK that one character takes 80 microseconds, 20 take over a millisecond. There can be also other things like long computations for each list item. There can be list items that maybe can sum up if you have a user, and instead of queuing 1 or 10, it may go on and queue 100 or 5,000. Processing them all with disabled interrupts leads up to long latencies. Another thing are contented locks with ROS bin locks. Basically, you have CPUs, systems with a lot of CPUs like 64 and up, and all of them are spinning on the same lock. The lock will be handed over from one CPU to the other, and all that will increase latencies by the way that the last CPU has to wait the longest. It's still fair from that point of view, but waiting 50, 80 microseconds for the lock is just killing the system. This is an example for clock nanosleep. Clock nanosleep is invoked for a task to sleep, and once the time is up, the task is woken up. In general, for SCAD-ADA, like the normal task, we try to shift them to soft IRQ context, which is preemptible. But an RT task itself is woken up from hard IRQ context, which disabled interrupts and so on. The first one wakes up 100 tasks, and this is an output from the cyclic test. So the important part is that the task itself runs at priority 95, is like very high in the system. And while waking up 100 tasks, we get a maximum latency of 26 microseconds. And since current is completely something else, it means that the system didn't even notice it, that this woke up 100 tasks simultaneously. If we go up for 500 tasks, we end up with 75 microseconds, at which point it becomes noticeable. So you see that something is odd. And if we go on with 5,000 tasks, we end up with over 4 milliseconds, at which point it's killing it. And this is completely controlled from user land. So waking up tasks at the same time is actually not working for RT, because all the wake-ups are performed at the same time. And this is basically what I meant with, you have a list item, you work on it with disabled interrupts, and you go one by one, which is basically happening here. It wakes one task by one, and 5,000 is basically killing it. Priority boosting, basically inheritance. It is one of the core things we need in RT, that one task that has a lock can hand over the lock to the RT task which has higher priority, and the handout box move in a way that the priority is handed over. And basically how it looks like is something like this. This is a compressed tracing output, where basically remove everything so to make it fitting on the one slide. So we have two tasks like locking A and locking B. And locking A did acquire the lock, and then it woke up locking B, which is the other task. And task B, locking B, was scheduled immediately on the CPU because it has the higher priority. And locking B requires the same lock as lock A is currently holding. And since it has the higher priority, it can never be running on the CPU again. And to avoid the situation of spin for error, we basically hand over the priority to the task with the lock, and then locking B leaves the CPU. Basically, so locking A can make progress as long as it has the lock, and then it can release the lock, so locking A can still make progress in a good way and do whatever it needs. So the cat PI set prio is where you see that the priority has been handed over, and once the lock has been released, the priority is getting back to the original task, and locking A remains running with the low priority again. And this is an important concept that we have, and we have it for most locks in the kernel. Basically, everything that is based on RT mutex, the original implementation of it, and this is like most of the kernel that we have in it. The important part is that there is always one lock owner, and we have the owner recorded, so we can hand over the lock one way or another. We have RVSEM, for instance, where it is not really working perfectly. The reason is that RVSEM can have multiple readers, and we cannot boost all of them to get them out for the writer. So the writer is always waiting for all the read to get out. From RT point of view, this doesn't matter much, since the reader is usually that task in the system that has the high priority. So the reader can hand over its priority to the writer and get it out of the critical section, where it doesn't work the other way around. Same thing with RW-lock-T. Most of the users gone or transformed to RCU locking, where it's basically lockless. So from RT point of view, it doesn't matter much. Semaphores, for instance, don't work at all, since they are completely anonymous. There is no owner. You can acquire the semaphore in one thread context and release it on the other. And since there is no owner tracking, nothing, you cannot do anything about it. The MM semaphore is one of those that was offending in the past, but since we have no memory allocation for the RT thread, we basically ask people to allocate memory up front and lock the pages in memory with mlock. Then it doesn't happen actually. With that, we end up in a situation where one thread can still run while the other thread in the same task can still allocate memory. So this is basically working fine. PI boosting can also be used from userland with the prior inherited mode. Right. Soft-IO context. We had, since the early days of RT, several iterations of it, what to do, how to handle it. We had one way where we were locking one soft-IO against the other, and we basically were following networking, because networking came always with other things how to break us. At which point, later we decided to follow mainline principle of doing it. So basically, we ended up with a big kernel lock, with a kernel lock per CPU, which is basically what soft-IO does. The problem is that NetTX soft LQ and tasklet, for instance, are completely unrelated. Like NetTX soft LQ is doing networking processing, while tasklet can be some work offloaded from an SATA driver, like completely different department. However, they can still be related, like NetTX and RX can share the same per CPU variables. And networking sometimes expects that the timer isn't running on the same CPU. And for that reason, we had to follow up with it. And the problem we have is that if you have, for instance, large networking processing with Ethernet driver, which does downloading, sending packets over it, and then you have a CAN driver which tries to send only one tiny packet, that driver has to wait for the soft LQ to become available, at which point it means he has to flush all the way and wait for the networking to be done. So PI and everything from priority boosting is working, but it still takes time to wait until it's finished its work, which is kind of breaking things if you want to have low latency. The way we tackle it right now is that we try to offload things. We have like the high throughput for networking, like on one CPU, and the dedicated CAN with the low latency is running on other CPU. But it's not ideal that what we do right now. Another thing is the part that we dispatch work for later. This was very common in the early days where we didn't have threaded interrupts. So basically, the interrupt handler that was running with disabled interrupts had some work that it wanted to hand over later within the tasklet, where it can run again for longer periods of time with enabled interrupts and not affect the system as much. A famous example is mostly the NAPI for networking, where the interrupt handler basically schedules the NAPI handler, which runs later in soft IRQ and basically collects packets from networking card. As mentioned earlier, the more tasklets you get, the more work you have in some way anonymous context, where we cannot hand over priorities. We cannot steer the work and say, this is more important than that. So in general, the nice thing to do from our RT point of view is to avoid tasklets and use the threaded interrupt for the work. It still has the same benefit, mostly that it runs with enabled interrupts and can be visible, and you can see where it's coming from. Where if you have a tasklet scheduled from the disk I/O, another one from the video driver, like a webcam, you don't see which one is which. You basically see the task that you have a lot of soft IQs going on in the system. Another way we see is like work queues is basically the same mechanism where people hand over work that is not done yet. It's basically handed over to a K worker. We end up mostly in the same situation that we cannot track work. And a famous example is the TTY layer, where you do TTY communication, read and write. We start in the interrupt handler where we can assign a priority and say, this is important, this is high priority. But then the TTY layer schedules a worker to complete the injections in the TTY buffer, at which points it ends up in the K worker, and and it's basically anonymous. And the problem here is if you have a RT system and you want to have high priority console work, not maybe console, but maybe Bluetooth or a dedicated device on the other line of the TTY, then it basically breaks the thing. And there was discussion in the past how to fix it, and we never ended up with anything. I'm aware that a lot of people having their own hacks to avoid a Kai worker and have a dedicated thread for it. But using more worker from an interrupt handler for dealing things with a single device is not ideal. It even hurts more the system if you hand over the worker to a dedicated CPU for no obvious reason. And the point is that if you're using RT with a dedicated CPU, you don't see where the work is going, and you maybe hurt the isolated CPU. So with that, I'm getting to the end. We're basically trying to mention all the things that RT can be broken with. Most famously, the raw locking and the atomic contacts, which should be avoided if possible, if not needed. So we try to have it for the hardware to begin with and avoid it if not possible. Also, the API that we have is very limited. Like memory allocation is not working, task waking is working as long as not the awake queue. Same with PM disable, be careful. All of that contributes to high latency if it's taken for a long time. Spinning locks, which are high contended, especially on many CPUs, will raise the latency while all the CPUs try to get the lock independent. They spin with disabled interrupts or preemption, and you cannot interrupt them at all. And if you come up and you think you need to invent a new primitive for locking, for data structure, whatever, keep in mind that you maybe need a synchronization for RT in case it's something like polling to complete, as I mentioned with the timer. You need to keep in mind that RT will preempt you and you need to tackle it. Keep in mind if you need boosting or not in case to make progress faster. And soft IRQs, be aware that currently we have a big kernel lock for it on a per CPU basis. And this ends up in not ideal workloads. Now, so with that, I'm coming to an end. Any questions?
Yes. So, I guess, no, I think you may have already gotten this feedback already, but so recently I was doing some stuff on ptrace and some preempt RT patches came through, and how do I put this? There used to be, and I think it really should still be, that preempt RT changes can't happen in mainline unless they're good for mainline, maintainable in mainline.
Right.
And I've seen a lot of preempt RT patches, maybe that seem to be, oh, we got to do this or preempt RT doesn't work. And that's the justification. And it's not particularly good patches for mainline. I guess making this a question, have you heard that feedback? Have you seen that happening?
Yeah, a few times, yes.
Okay, yeah. I just want to give a little pushback because that was, it's still, the ptrace stuff still hasn't gotten sorted out, and the patches I've seen suggested are still not.
Again, please.
The ptrace issues haven't been fully sorted out with preempt RT, and the patches I've seen suggested are all hacks that are not good for maintenance of mainline. So, just wanted to make certain people dealing with preempt RT are aware of that.
Yeah, ptrace is, I think, one of the examples where it's actually hard to get. I am not aware how ideal the non-RT version of ptrace is. And from RT point of view, it works mostly, and I think we ended up with a few hacks in the end. But mostly after a rewrite from, I think the ptrace maintainer is going to put it that way.
Me.
Right.
Yeah. I there's still, well, me and Oleg does more, but yeah, I kind of poke. But yeah, I did a lot of sorting out, but yeah, ptrace is a pain because it is one of the few cases in the kernel where you have to stop in the scheduler. So right. You can read all the process state remotely. And that has a whole bunch of special rules. And, by preempting stuff, stuff was thought, anyway. Yeah. During spin locks and other stuff, it gets a whole kind of weird rule stuff.
But not to be offending, P-trace is kind of difficult to understand from people that are not been around for years to understand how it got where it is right now.
Oh, yeah.
So we never mean to throw patches at you and say, this is what we want and this has to go as in, right? So we basically often schedule an idea how we propose to do things, and sometimes we're not happy with it either. Now, if people step in with more knowledge and say, this is what needs to be done, we need to rewrite this and that, it may take weeks, but this is what I want to see. In general, we are happy to follow up.
Okay. Yeah. Just the way it was presented was, P-trace is broken here. We got to do something.
Exactly.
It's a regression, something, that kind of language, when in fact doesn't even, it's never worked. It's always been broken.
Exactly.
And what needs to be done is dig in and find a good solution that's maintainable for everybody.
Exactly. So networking or anything else where we are more familiar with, we come up with something that is closer, where the maintainer doesn't shoot us down completely. And then they say, this is good, but please do it that and that, and then consider these cases as well. And then clean up and do whatever you want. So this is the way we've been working ever since. So if you see us posting patches that are completely nuts, just say what you want. Okay. And we usually follow up. As I said, the different part with P-trace is that we never understood what it tries to protect, how it works, and what is meant to work. Or how, yeah. So if you can clarify that and say what you want, usually we're happy to follow up.
Yeah, and it just has, P-trace has so much history, I'm not certain anybody has it in their head, and you just have to read the code a lot. So, but yeah. Anyway.
Right. I mean, after you reworked, we went down from, I think, 3 or 4 P-trace hacks down to 1.
Yeah.
Yeah, exactly. Yeah. So thank you very much for that. Anyone?
Yeah, can I?
Go on.
I would like to point out that the locking types documentation in the kernel is up to date and fantastic, because even though I'm doing this stuff all the time, I also sometimes forget in this preemption models, bin locks or this or that. Just to throw it out there, the locking types documentation is fantastic with examples so that people can reference that. My question is your experience, because it's now the job of the maintainers of the subsystems to make sure, when preempt RT is mainline, to kind of filter to make sure that we don't have this lock abuse or incorrect locking. I was just wondering what your experiences is for the maintainers. Are they following this, or are you getting lots of questions, or in general, are the maintainers okay with the new locking types, that they understand how preempt RT changes things?
I think over time we have now more understanding than we did before, and I think the document helped a lot. Not a lot of people are offended and say RT is not what we want, it makes things complicated. And that's why we try to contain it to small pieces and remain the API working as is. I mean, the sec count API is an example for it, where we had way more hacks before it, and with the rewrite, it went nicely with additional debug code, which RT is abusing or using for its own benefit. And so as long as we stay hidden behind it, people are usually not offended. And yeah, things like red interrupts are always there, so people try to respect it. So that's not RT only thing. So that's usually try to work with. We good? Thank you very much.
Okay, we just uploaded. There you are. Just in case. Oh, Beamer, right. Wait.
Oh, sorry.
Yeah, it's just uploading. Okay, I think it should be quick because it's PDF, so
Yep.
there's no conversion.
That's what I hope. And there's no USB port. Ah.
So, just, are you ready, right? Are you ready? Yeah. Okay, so Josh is going to present spawning processes faster and easier with IO U-Ring, and I think he will introduce himself, so I let you do it. Thank you, Josh.
Thanks, Miguel. So I'm Josh Triplett. I've been to Plumbers a few times in the past. It's been a while. It's nice to be at an in-person event again. I work on quite a variety of things these days, most notably quite a bit of work on Rust, but I'm back to doing a little bit of work on the kernel. So I am doing a lot of work on build systems lately. And one thing build systems are known for is that they spawn a huge number of processes. And so I care about launching processes quickly. So let's talk a little bit about how a process normally gets launched on a Unix system. So for some people in the room and some people online, this is likely to be a little bit of review, but bear with me, we'll get to the novel stuff reasonably soon. So when you're launching a new process, you have a variety of bits of setup that you want to do before you actually exec the new process. Everything from redirection and file descriptors to priorities to CPU affinities to masking signals to permissions, UID and GID, to what your root is, to setting up a whole container with namespaces, setcomp filters, everything. So you need to do some kind of setup before you launch, which is one of several reasons to, you need some code to do that setup before you launch. Where is that code going to come from? And one answer for that is, well, it comes from the current process. So one way to do that is with the standard model of fork and exec. So with fork, you create a copy on write copy of the current process. And copy on write does not copy all of the memory of the process. It just copies all of the page metadata of the process. And then exec will promptly throw away that copy and replace it with a new program. If that sounds slightly wasteful, that's because it's slightly wasteful. So how expensive is fork, though? So for that, I want to talk a bit about the benchmarking setup that I'm going to be using for the entire talk. So I create a pipe. I read the start time right before starting a process. I spawn a child process using a path search to make it more realistic via whatever method I'm trying to test. The child writes the only thing it does in an optimized bit of assembly is write the end time to a pipe and then exit. And then the parent process will block reading that time from the pipe, compute how small that was, and then it will capture whatever the minimum time was from 2,000 runs. The reason here for minimum rather than average is that if it's possible to do it that fast, then everything else is almost certainly overhead, whether that's a context switch or something else that went on during that particular interval. So I'm capturing how fast it's possible to do. So with that in mind, the baseline for a fork, at least on my laptop, was 52 microseconds to successfully do a fork and launch the new process and then get the time in the new process. So last instruction before doing the fork, to first instruction running in the new process, approximately. But that's the baseline. What if you actually have some memory allocated? Well, if you have a gig of memory allocated, that's still not that many page frames, and fork does a little bit worse, but okay, an extra 4 microseconds to try to fork a larger process doesn't sound terrible. Except it turns out Linux has some really clever optimizations here, and they help you in some cases. Most programs allocate a lot of memory that they don't use. And so Linux doesn't bother filling in the details unless you actually use the memory. So what happens if you do allocate the memory and then do actually use it? Well, then it gets a little bit worse. If you go touch every one of those pages, we get well over 100 times worse, and you're talking 7.5 milliseconds to successfully fork a process. So this is one of many reasons that some libraries and systems suggest forking off at the beginning of your program and having a little helper process that just exists to fork more processes, that kind of thing. But that's logistically obnoxious and all sorts of problems. So we can do better than this, and we will. So performance isn't the only problem with fork, though. Obviously, performance is something I care about a great deal, but there's a lot of other issues as well. First of all, multi-threading. A lot of programs tend to be multi-threaded, and fork interacts really badly with threads, because any lock that's held by any other thread will remain held forever in the child. The fork only copies the current thread, which is what it's supposed to do. You don't want multiple copies of other threads continuing on. They don't know what you're in the middle of. All of the memory is copied identically, so any internal state and any locks is just copied identically. So if you call any library function almost, you could just deadlock. That includes things like I/O or really basic things. There's a list in the signal safety man page, which people don't tend to read before they use fork for the first time, and hopefully you don't encounter it for the first time when you're doing horrible debugging of deadlocks. But it includes a reasonable number of things you would commonly expect. It doesn't include some things you would really expect, like, for instance, change root or set priority. So if you are in a multi-threaded program and you do a fork, you're not actually allowed by the standard to change the root device to try to improve permissions. You're not allowed to renice the process. Quite a number of other things, let alone things like setting up namespaces and similar. So it's really not a very good option in a multi-threaded program at all. So as long as we're talking about things that are terribly broken, let's talk about vfork. So vfork creates a child that borrows the current process rather than a copy of it, and then the parent process will simply wait until the child is finishing borrowing it and then take it back and use it. So borrows the current process. What in the world does that mean? We'll get back to that. So how fast is vfork then? If it's terribly broken, let's at least hope it's broken and fast, right? Well, that it is. It manages to be quite a bit faster than fork, and not only that, it really doesn't take any substantial penalty from having a lot of allocated memory, because it's not even copying the page frames. It's just saying, well, let me point to your entire address space and I'll just use that. So what are you allowed to do after a vfork? Well, very little, as it turns out. You can exec, you can exit, and that's the complete list. Also, you can't write to any memory, including the local stack, except for a PID variable, and you better not return or call anything. So you really can't do any setup at all. This is not actually helping with any of our other problems. So what does it actually mean that it's borrowing the current process to have all of those restrictions? So vfork is effectively creating a thread with absolutely no synchronization that runs with the same stack as the parent. And at this point, the seismographs all over the world should be picking up the collective shudder from this room and from all of the remote attendees. So I hope you didn't actually need any setup code for this. But not only that, how sure are you that your compiled code didn't use the stack? What if your child process receives a signal among the many things that can go horribly wrong? And so libraries try to work around this, but for the most part, they just don't use vfork. So in an effort to fix this, POSIX introduced the POSIX spawn call. It was one call to spawn a process rather than multiple calls, spawn a process and then do setup and then actually launch the process, the executable you want. It was created originally as well for systems that couldn't fork at all, things that didn't have an MMU. And effectively, it hands the problem to the C library. It says, okay, you figure it out. Do something sensible here that will be reasonably fast and will be functional and get all these things done. So you're not actually allowed to have setup code here. You get a ton of configuration options, and you'd better hope that those are sufficient. And then there's some non-portable extensions to those options that can make it slightly better. But if it doesn't do what you want, you just can't use it, and you have to go back to fork and exec. So it has a POSIX spawn file actions T, which is where you can put all of the please close this file descriptor or dupe this file descriptor to that one, so that you can do redirections and similar setup. It has spawn arrow T, so you can do things like priority and affinity and similar if it has what you need for that, and that's it. So glibc implements this by using a somewhat safer version of vfork, in that it uses its own stack and blocks all signals, which solves some of the problems that can go wrong with vfork. And this, unfortunately, manages to make it somewhat less performant than vfork, but still somewhat better than fork. So in practice, it's a little faster than fork rather. And it again does not take any real substantial penalty from how much memory you have allocated. At this point, the variations between those three tend to just be noise. So let's go back to the original question. Why do we actually need a copy of the process in the first place? Well, what we needed was setup code for a new process. We need that setup code to live somewhere. Fork lets that setup code be in the existing processes code. vfork doesn't let you have setup code at all. POSIX spawn gives you specific setup operations, and you've got to hope that's all that you need. So let's talk about something else for a moment. Let's talk about IOU ring, which is likely what you're here to see used. So what does IOU ring do? Well, it provides shared memory communication with the kernel. It provides a pair of ring buffers, a submission queue and a completion queue. Here's work I want the kernel to do, and the kernel says, here's work that you've told me to do that I've done. It's very similar to protocols like NVMe and VirtIO. All of these are high-performance communication protocols between two devices that can run more or less independently, and this works the same way, treating user space and kernel as two different going concerns that are running concurrently. It avoids the kernel entry and exit overhead, which that's always been a benefit. It became a much huger benefit with all of the speculative execution vulnerabilities and all the other reasons that kernel entry and exit has become even more expensive. And for our purposes, one important detail is that it supports linked operations. So you can tell IOU ring, here's 20 things I want you to do. And it can tell you, okay, did that, that one failed, did that one failed, that one failed. But sometimes you actually want to say, well, if this one fails, I don't want you to do the next one at all. And sometimes you want to say, okay, it's okay if one fails, go on and do the next one, but I don't want you to do these out of order because I'm opening a file and then I want to do something with the file, so don't try to do something with it before you open it. That kind of thing. So it supports two different kinds of linking. You can create a standard link which just says do these things in order, and you can create a hard link which says do these things in order, and if one of them fails, don't do the rest. So now we have a way of specifying a chunk of operations. What if we used that for process setup and launch? We could provide a ring of linked operations, and we don't actually need a user space here. A kernel task doesn't need to have a corresponding user space. It can just do work, and then when it's done, well, hey, it had something to exec, so it doesn't have a user space to replace. There's nothing to throw away. So I added a couple of new IOU ring operations. First, I added IOU ring op clone, which captures a series of linked operations. And instead of running them on the ring itself, it creates a new task as quickly as it can, and it runs the operations there in the link. And then ioring op exec will create a new program in the current task, and it will skip all the remaining operations in the ring if it succeeds. Otherwise, it'll continue on if it's not hard linked. And these are actually independent operations. You could theoretically clone and do more operations in a new task and not exec. And more importantly, you could actually exec without cloning if you're trying to replace the current process. So if you're doing everything else with IOUing anyway, you could also do a series of operations, replace your current process, and not have to come back to user space to do that. But the main use of these is to work together. So if an IOU ring, if an operation clone runs out of linked operations and it falls off the end of the ring, well, it doesn't have any user space. So if it falls off the end of the ring, it will sig kill itself rather than returning to user space that isn't there. An IO ring op exec will skip any further operations in the ring. This is actually really important for security purposes because otherwise it would be really trivial to build a security vulnerability. Exec a set UID program, then before returning to user space, read into user space and write data to particular addresses, then return to user space. Let's see what happens. So if you exec, you need to immediately stop and return to user space and let it run. But if you're not successful execing, then as long as you're not hard linked, you can keep going. And there's an important reason for this, which is path search. If you've ever done an S-trace on a program that's doing a path search and trying to run something on your path, it doesn't go look to see what exists. It will just fork and then try executing in the first place, then in the second place, then in the third, then in the fourth. So if you see in your programs a fork followed by half a dozen execs or more if your path is longer, this is the reason. It's searching the path, and the first one it hits, it succeeds and doesn't come back. So we're doing the same thing, but we don't leave the kernel and we don't have as much overhead for each exec. We just do a series of operations, and then the first one that succeeds, we stop the rest of the ring. So this has some other advantages, not just performance. This actually completely bypasses any need for libc wrappers because there is no user space here. So you don't have to deal with any of the user space complexity, and it is considerable, that surrounds fork and especially vfork. Vfork always has to be written in assembly because it is extremely intricate and careful to avoid actually returning. Fork can technically be written in C, but it still has a lot of weirdness it has to deal with in the compiler. Things like, well, this thing is going to actually return twice, once in the child process, once in the parent process with two different values. It needs to be careful about what state that it stores. And in general, fork is something the library has to be fairly careful about. Plus, the C library has a lot of work that it does around fork to try to minimize the issues I mentioned earlier. If it copies all of memory, including internal state, it could very easily deadlock. And so there's a whole at fork mechanism. There's a pthread at fork as well as internal mechanisms used in the C libraries just to try to improve the safety of fork and do a little cleanup before you fork. But we can skip all that because we don't have any user space to copy. We're just running exclusively in the kernel. This works perfectly in multi-threaded programs. There's no issue with it at all because, again, there's no state that you're sharing and copying. Now, you have to have the same precautions you have using fork in the multi-threaded program in one sense, in that you don't want to open a new file on another thread that isn't clo-exec and at the same time be launching a new process because you could end up accidentally leaking that file descriptor into the child. But that's the normal precaution you need to take in general, and you should really be opening every file descriptor with clo-exec most of the time. So I wanted to show an example of what this actually looks like, because sometimes you see discussions of IOU ring and it's, oh, IOU ring can do this and it can do this quickly, but you don't actually see what the code looks like. And so I wanted to make it really clear that IOU ring, and in particular libu ring, makes this remarkably simple to do. So this really just looks like get a submission queue entry, an SQE, prep it to do a clone operation, and set its flags to be linked so that the next operation will be part of the clone. Get another submission queue entry, prep it for an exec with the standard arguments of what's argv0, what's argv, what's the environment, and then submit the ring. And you can do a larger version of this. You could prep half a dozen execs in a row for doing a path search. You could do some dupes and some closes and other operations before your exec. But in general, IOU ring is not any more complicated to use than this. Get a submission queue entry, prep it for a particular operation, possibly set some flags, submit it. And then on the other end, later, you can look at the completion queue if you want to see the answers. So this is really useful for reasons other than just performance. Like I said, it works great in multi-threaded code. It's frankly simpler to use than some of the things like POSIX spawn. So with all those caveats that I'm giving of being useful for without performance, then maybe I got disappointing results from performance and I'm trying to provide caveats and couch that a little bit. Actually, it turns out it's faster across the board. So it's actually faster than vfork, let alone POSIX spawn, despite being much, much safer to use than vfork and letting you do setup code. So this is the fastest available way to launch a process now. And I'm planning on submitting this upstream as soon as I get it cleaned up a little bit more and work with Jens enough to determine the right stopping point between making it faster and faster and faster and actually getting it upstream. So right now it's 6 to 10% faster than vfork. It's wildly safer and more flexible than vfork. It's 31 to 36% faster than POSIX spawn. And frankly, just getting started at this point. So it could get a great deal faster. There's a lot of optimization to be done. So next steps, first of all, POSIX spawn itself could be implemented using this in the C library. As long as we have all the operations that it needs, we map each one to a submission queue entry. We submit the whole thing as a batch. And if for some reason we don't support all the operations of POSIX spawn yet, we could always fall back to what it does currently. But as long as we can map all the operations in the spawn's batch set of operations, we could run it as a single IOU ring queue and speed up all existing process launches by somewhere around 30%, hopefully. One optimization that Jens and I are working on right now is supporting a pre-spawned process pool. So if you know you're going to be launching a variety of processes, or even if you know you're going to be launching them one at a time, but you know you'll be launching several, then you could warm up a process already, have it ready, and then when you go to launch a process, you already have one, you just say, please exec this. We can optimize clone quite a bit further. Right now, I'm just using the same interface that other kernel clones use, but it may well turn out that you don't need to create as much of the associated user space because you're about to throw it away and replace it anyway. And one experiment I'd like to get to is just setting up a process from scratch, not copying the existing user space, not copying the majority of the process. You still need to copy a few bits across, especially permissions and similar. But for instance, rather than copying the current file table, just set up the file table from scratch by filling in IOU rings, pre-registered file descriptors and saying, this file descriptor should be 0, this one will become 1, this one will become 2. So as a quick aside, I wanted to mention, while trying to create the fastest way to spawn processes, I also managed to create something you can use today if you don't mind about the same unsafety as vfork, a little bit safer and still faster. It turns out you can also call clone and use clone VM without actually creating a thread. So there are two separate flags to clone. There's clone VM, which says share my address space. And then there's clone thread, which says make me a thread in this process. If you don't call that, if you just use clone VM and not clone thread, what you get is something that's sharing your address space, but is technically a separate process, so that if you exec, you don't replace your current process, you replace that new process you've just created. And this is effectively as fast as what vfork is doing because it's not copying the current address space. But clone makes it easier to give it a separate stack and do some of the similar things that glibc and others are already doing to make vfork safer. You could similarly clear all the signal handlers and make sure it doesn't take a signal. And it's still not as safe. There's still some things that can go wrong, but this goes almost as fast as the current version of IOU ring, but I expect to leave it in the dust later. but far be it for me to leave out something else that's almost as fast as this that came up in the course of finding this. I also wanted to give an acknowledgement to Jens, who I think is in the audience at the moment. Hey, Jens. So, who has been incredibly enthusiastic about this. So in addition to creating IOU-ring in the first place, Jens has been excited about this since the moment I introduced it and has been chomping at the bit to poke at it, make it faster, and at some point I had to say, okay, I have to actually write the talk before we add more cool things to this. So as soon as this talk is done, I expect to not have that constraint and to properly start working on making it even better. So thanks, Jens. So I'm Josh_Triplet on Twitter. I do this work and a lot of other work, including Rust and build systems, thanks to GitHub sponsors and other things like that. I am working on build systems for a startup called Build It, and I'm happy to take any questions at this point. Thanks, everybody.
Hey, Josh. This is great. We could really use this. We want to switch a lot in systemd, for example. We want to switch the main loop to use IOU-ring, and this would be extremely helpful for this case as well. And funny enough, I worked on something similar a while ago. We would need to move a lot more setup operations into IOU-ring as well, right? So because as you listed, we want to do a lot of setup and stuff and so on, which means you need to have a lot of synchronous system calls and operations in IOU-ring. Are you planning to do this?
So I think it makes a lot of sense to have almost any syscall in IOU-ring that would make sense in setup. At one point, IOU-ring, I believe, was focused much more on things that could be split into an asynchronous portion, but it does have the ability to throw things onto a separate task to get them done for things that can't be done asynchronously. But more importantly, this approach is creating a brand new task for the purposes of running the contents of the ring, the linked operations in this clone, which means if you're running a synchronous operation, you're not slowing down the rest of the ring or any other operations you're doing. You're just making your process spawn take a little longer. So I personally think it would make sense to add anything you could possibly need to launch a process in this. That's a pretty broad brush, and I'd be interested to know what you're potentially looking to add, but I'd be excited to see it. But I'm not the person you need to convince on that one. Yeah, no, I will happily go on record as saying I would love to see a kernel that has exactly 2 system calls, IOU-ring setup and IOU-ring submit. I would love to see how that would work and just leave everything else out. But that's a problem for another day.
How do you see this interacting with the LSMs and seccomp?
Exactly as well as IOU-ring does today, which is to say if you have the appropriate LSM hooks and they don't slow down IOU-ring, then I would expect them to continue working just as well. I don't anticipate that being an issue at the moment.
You mentioned the new task created with the IOU-ring clone doesn't have a user space. Do you mean it doesn't have an MM? Or does it transiently share the MM of the task which cloned it?
I'm sorry, I caught about half of that. You're talking about sharing an MM?
Yeah, when you clone the process via your new IOU-ring clone operation, you said the new task does not have a user space at that point. Does it have an MM at all?
So at the moment, it does have an MM for a specific reason. I'm currently using effectively clone VM to give it the same MM as the user space that created that process to begin with. And the specific reason for that is that when you're doing IOU-ring operations, many of them would access a buffer that's stored in user space. So if you did a read or a write, or for that matter, the exec operation itself takes a pointer to the argv and the envp in user space, and so it needs some MM to work with. So for right now, it uses the same MM, but unlike vfork, that's not completely unsafe and ridiculous because it's inside the kernel. It's normal that you have kernel and user space sharing the same MM. What I'm hoping to do eventually is add a flag to the IO-ring op clone that is, no, really, I'm not going to touch any user space buffer in this. in which case you could actually have no MM until you create the new process.
Okay.
But then you would have to use things like registered buffers, registered file descriptors. You'd even have to use a registered buffer or similar for the exec itself, or actually my preferred alternative there would be to use an F exec. But regardless, right now it's using the same MM.
Sure thing. Just my reason for asking is just as a note of caution, there's a bunch of code in the kernel which assumes that having an MN means you have a user space task and vice versa, which would need to be cleaned up and fixed before you could do that. But otherwise, great.
No, that sounds like an excellent example of the kind of thing that I want to make sure to fix before this actually goes into the kernel. This is very much benchmark quality prototype code, and I would like to hammer on it a great deal before it goes into the kernel. Next question. Also, are there any questions online that I'm missing, by the way?
Got one more in the room if you're not busy with online questions.
That'll take a moment to launch, so go ahead for another one in the room.
So we've had some challenges interfacing the LSM and IOU ring together. It hasn't always worked as smoothly as you kind of alluded to. So I would just ask, when you get ready to start posting these to the upstream mailing list, please include the LSM mailing list so that we can be part of this discussion from the beginning and we don't have to bolt stuff on at the end.
I would be happy to include anybody who'd be interested in this. Please send me a note with the appropriate places you'd like me to include in the first round of like patch v0, and I would be happy to copy extra things. For my part, I am happy to make sure that all the appropriate hooks and similar are in place as long as they don't, make the performance point of using IOU ring irrelevant. But yeah, I do want to make sure that we do actually capture all of the appropriate security hooks. On the screen, yes. Would it be a problem for checkpoint restarting user space to dump a process in the middle of performing a long IOU ring chain? Also, we do use clone VM in CRIU. So the best answer I can give to that is I don't know. I don't know if CRIU has the ability to capture something in the middle of an IOU ring chain. I'm getting a head shake from Jens in the room, so it sounds like, yes, it would probably be a problem.
Yeah, there's not support for a full ring state and everything. I don't think that currently exists.
Oh, right, sorry. The question is on here by text, and, oh, you mean what Jens was just saying? Sorry. So Jens was saying there is not currently any support in CRIU for dumping the current state of IOU ring so that it can restore in the middle of a long chain. So that would need some additional support. It sounds like that's not specific to IOU ring spawn. That's an issue with IOU ring in general.
Yeah, there is a Google Summer of Code project that we usually put out for CRIU to make it dumpable make IOU ring dumpable in CRIU. So if somebody wants to work on it.
Sounds great. So if anybody wants to work on that for a Google Summer of Code project, or hopefully work with someone on that, because I imagine that would be a fairly complex project. But,
We would need an IOU
yeah,
ring
that sounds
expert.
incredibly helpful.
We'd need an IOU ring expert.
I would imagine so, yes.
Hello, and nice talk. And I anticipate such a work could be incorporated by distros and many build systems, maybe in a relatively short time period. But as I understand it, the whole IOU ring spawn machinery works by creating a new global state. It needs its own IOU ring queue to function. Yeah, so it's basically something introduced beneath a user process, so the process might not be aware of its existence. So this might interfere with some security mechanisms, like with I imagine system D's service sandbox. It might not have the system call allowed, or maybe some seccomp filters that might not anticipate such a use. So there might be some compatibility problems or downstream distro modifications that might be required for downstreams to generally adapt to this. And yeah, is this a problem? And how do you plan to somehow make downstream's life easier? Thanks.
Sure. So there's a couple of different answers to that. It is definitely the case that any new underlying mechanism of doing something could potentially provide a surprise to something that's trying to provide a sandbox on the basis of the exact operations expected. This is honestly a standard problem even without IOU ring, where just one of the C libraries changes the exact implementation syscall that it uses for a higher level library call, and all of a sudden setcomp filters start failing across your system, and you need to figure out either do you add something new to the setcomp filter, do you revert the change, all sorts of issues like that. So this is not a problem unique to IOU ring, but it definitely applies to IOU ring insofar as it is not as straightforward to provide the same level of filtration for an IOU ring syscall. I would expect that full integration between setcomp and IOU ring would potentially help there, insofar as it would be nice if you could specify a filter once and then have it implicitly encompass doing the same thing via IOU ring if you also allowed the IOU ring syscalls. So it's a reasonable question. I don't know a perfect answer. I think that at a minimum, at least for the foreseeable future, for the next handful of years and for longer for software that has wider compatibility windows, software is likely to have fallback mechanisms for if IOU ring is not available or if a specific operation is not available. So I would expect if those operations are blocked, then user space will still work. But of course, that's not ideal because you want it to be able to get the full performance as well. So what I would hope would be some better integration with setcomp filters that, again, balances between how do we do this as rapidly as possible and how do we provide the same level of protection. Does that answer your question? Okay, awesome.
One more quick question. If you, I wanted to ask about the performance numbers. So obviously there might be use cases where not the IOU ring isn't used for a long time. It's literally just used for clone and exec, and so to set up a process. For example, I can see this in libc. So other performance numbers, including the creation of the ring and destroying of the ring, or just the clone and exec operation?
So that's a reasonable question. So these numbers are not including the ring setup and teardown at all. I could certainly measure that for the next round of numbers, and that's a great idea for the ultimate submission of this patch series. That said, I would also anticipate that if you are adding IOU ring support to some existing library, whether you're doing something like POSIX spawn or similar, once there is support for doing IOU ring there, it would make a huge amount of sense to use that as the backend for other operations as well.
Yeah, I mean, for example, for an event loop type style, where you then definitely you will have the ring, you use it for your event loop, you also use it for clone and exec, absolutely. But I can also see a use case for this to implement POSIX spawn in libc through IOU ring.
Right, and I would say, if I were to take a wild guess, I don't have the numbers off the top of my head, I would be surprised if this pays off if you literally launch only one process.
Yep.
But at the same time, many things that are launching I don't know that this would necessarily make sense if you're one of the adverbial programs whose job is to make 3 syscalls and then do an exec.
Yep.
But on the other hand, I think it makes a lot of sense if you are launching multiple processes. So I think this makes a lot of sense if you are make or CMake or something similar to that. And then the other aspect of this is, frankly, at some point I would love to see a liburing backed C library that just uses this for literally everything, in which case it would make a great deal of sense because it's already open.
I mean, the justifications for this implementation, in my opinion, are enough if you like just the use cases that you listed. I mean, and also.
Right. The fact that it is faster on an individual call and also works in multi-threaded programs and will hopefully support more operations than POSIX spawn. Yeah, I'm hoping that it's worth it whether or not performance is a win, but I would frankly expect it to be a win as long as you're doing more than one process launch, and I would have to benchmark it. I would bet it might be close if you're doing even one, but we should find out.
I mean, and shared libraries currently can use fork and vfork sensibly if they're running in a multi-threaded environment. It's, for example, one of the reasons why, I don't know, libsystem is multi-threaded and other libraries. So this would solve a huge amount of headaches for us.
Right. I'm also hoping that this will work in general for like anything that's using the zygote pattern of I've created a tiny little process whose job is to launch more processes. Hopefully this can do that job and save the effort, at least in some cases. Other questions either in the room or online? Okay. All right. If there aren't any other questions in the room, I just wanted to mention I am expecting over the course of the conference at some point to more or less sit aside and start doing more work on this and chatting about IOU Ring. So please catch me at any time during the conference, and I'm hoping to continue to be thinking of this, working on new ideas for it, brainstorming the next 10 ways it could be higher performance or better integrated with the system. At least one of the ideas came up about 3 or 4 a.m. last night for how to make the pre-launching even faster by and a little more flexible to use by letting user space manage it directly. Of let's launch a bunch of processes and say, I want this one to do this one to do this, and this one to do this, so it can sit there and wait for work for you to do. So that may be helpful, again, for things that launch a large number of processes. They could spawn a process, give it a handful of setup tasks, then tell it, okay, wait for me to make more copies of you in your setup state. So I would expect quite a few potential enhancements for this as well. Last call for questions. Okay, thank you very much.
All right, welcome everyone. I'll make this real quick. So we're gonna have a presentation by Len here on exercising the Linux scheduler with Yogini. And then afterwards, Julia Wall will be presenting about OS scheduling with Nest. A few just quick ground rules. If you are online, please make sure you have a headset with a mic, not speakers speaking into your mic. Otherwise, there's an audio feedback loop, all right? If you have any questions online, you want to post them in the chat. I will pick them up and I will repeat them verbally. Hopefully, I can parse your question and repeat it faithfully back to the speakers. There are some throwaway mics here. So those catch boxes, if you have any questions, both speakers have expressed the openness to take questions as they speak. So if you have any questions while somebody's speaking, please, raise your hand or something, and we'll take it as it goes. All right. Aside from that, go ahead, Lynn.
Testing 1, 2, 3. You can hear me. Many thanks to our sponsors, and also I'd like to thank our volunteers who are not sponsors but help us with their time and effort. Many of them, very impressive job they're doing, including teaching me how to use this system here. Let's see, let me get the right buttons for you. Okay. I'm Len Brown. I'm going to speak about a program that I call Yogini that I wrote upon the advent of, I work for Intel Corporation, and Intel has come out with some new chips, particularly for clients, which are hybrid CPU architecture, and that sparked my interest, or maybe my obligation, to pay attention to some more novel CPU topologies and how Linux handles them. My background is in power and performance, and so it's an interesting mix of power, performance, and scheduling where we're now playing. And so I thought maybe some tools would sort of pull some of these together and make this increasingly complex landscape a little more accessible, so that both in the design, the debug, the understanding, the tuning, all of this, a tool to get for more people to get their hands around this. Of course, the first person is for me, but when other people create stuff with this tool, that will be validation that it actually works. So I thought maybe integrating the generation of workloads, hardware and software observation, and report generation would be a handy thing to do. So what we're going to do here is I'm going to go through an example. Then I'm going to talk about how the program works. Then I'll go through another example. Pretty simple agenda. So to understand this example, first you need to understand the hardware that we're talking about. This is what Intel calls a 2+8 system. So it has 2 P cores and it has 2 E cores, all in blue. The P cores are multi-threaded. So from a user's point of view, this is 8, 9, 10, 11, 12 CPU system. Let's see, as of Linux 5.16, ITMT, which is how Linux schedules on this kind of processor, will spread to the P cores before using the HT siblings. So the HT siblings, those big half blue boxes, are what's used last, and the E cores are used in preference to those. And then, of course, where these yellow boxes are supposed to be processes actually, occupying those CPUs. This is called an Alder Lake processor. So this is a picture of 12 threads, which we might throw at that 12 CPU system. And the idea here is that, say 1 second apart after that first thread on the bottom, the pumpkin colored one starts. Say 1 second later, we start the red one, and a second after that, the yellow one, and a second after that, the green one, and so on. And then we have and then what we would like to observe is, where does the scheduler put these threads? We would expect, say, the pumpkin one here to be put onto a P core first, and then the red one to be put on a P core, and then The third thread we would expect to be put on an E core and so forth. And the last two we would expect to consume the HT siblings, sort of the CPUs of last resort. And then when the first two threads exit, we would expect them to vacate the HT siblings first and, you know, move things around such that the hardware is used in that way. All right, so this is one of the things that pops out of Yogini, and it says yes, we aced that test basically. So the way you read this, time is across. This is a 22-second experiment, and this is utilization basically. And so you can see the first bump in blue is utilizing. This is by kind of CPU. Blue is P core. And then the second bump is the second thread. The third bump, we start consuming the E cores, consume 8 of those, and when those are all consumed, then we consume the siblings, and then we start removing threads because it was FIFO in this experiment, and we vacate them basically in this order. So very simple, right? Okay, if you're an executive, we're done. If you're an engineer, there's some understanding to be had. Okay, so if you actually, so Yogini, this is we're using a built-in workload here, and the built-in workloads record how much work they're getting done. Okay, so this is a little more subtle because instead of just saying, hey, the CPU is busy, great. Well, how much applications really care about work they're getting done? They don't care about if the CPU is used or not. And so there's a couple of things jump out when you draw the picture this way. One is there's that funny dip in the middle. And then there's sort of this kink on the left-hand shoulder, or the shoulder further out by, 18 seconds. And so what's up with that? And things aren't as smooth as they might be. So if we draw this, since we've recorded by task and by CPU, I should mention here, since we're enumerating the CPUs, maybe I can, okay, well anyway, you can see the blue is P core 0, red is P core 1, which is its HT sibling. So the way this is rendered, that red guy's popped in the middle. Remember, he was the last guy to get used, okay? So so he wasn't on top of the pyramid before, he's just rendered this way. And similarly, yellow and green, yellow is basically the second P core, and green is his HT sibling. So they're used last. So it's copacetic. You can glean a couple of things from this. One is you can see how much work is now vertical, right? Not utilization. And so you can see how the P cores are getting more work done per time. These are like quarter-second intervals, 250 milliseconds. And you can notice some other subtle things. Anybody notice anything else subtle from this graph? Ricardo does, but he's shy. So if you look at the blue, it sort of dips down as soon as the yellow starts, right? It doesn't keep running getting as much work done as it used to. And you can also see the left, the 18-second, you can really see the dip, and you can see what happened. It seems that every CPU dipped, not just one CPU went slow, they all started to go in concert. And then you can see at the end, when the load starts to lighten, the sections get bigger, the CPUs start doing more work, okay? So that's interesting as well. And so this is a graph that Yogini spits out of tracking frequency, and ignore the noise. Basically, that's measuring frequency on effectively idle CPUs. So they're not too interesting, but you can glean at the very beginning of the graph, you can see, in this case, we're running at 4.2 gigahertz. And then as soon as we start the, in this case, I'm sorry, the colors change. It goes blue, red. Actually, the colors are the same. We're measuring the frequency of red, even though nothing's running on it. Remember, he's an HT sibling, so he's going to run at the same frequency as his peer, even though there's nothing running on it. That's why blue and red are up there. Not that something's actually running. Something's only running on the blue one. Then when yellow joins them, you can see the frequency of blue and red. So single core turbo goes from 4.2 gigahertz down to 4. And we don't really notice that on P core, on the E cores. When they cut in at 3 gigahertz immediately, and they don't go down until the dip where everything dips at 18 seconds. So that explains part of the strangeness we saw in the previous graph. We can also look at the uncore. The uncore is basically, effectively the bus on this processor. And it follows a similar pattern. So that tells us that something that's managing the uncore and all of CPUs is managing the frequency on us in concert. Okay, here's an eye chart for you. I'll give you I'll be interested to know if anybody can glean anything interesting from this mess of colors. So the first thing you want to look at is the highest thing, right? So this is the IPC, it's instructions per cycle per CPU. And you can see, well, okay, so let's start with blue and red. Well, blue and red and yellow and green, they all go along 2.2 instructions per cycle. Those are your P cores, the high line. The lower line is around 1.7. Those are all of your E cores. And the noise disappears as the E cores go from idle, where this is all sort of metastable, and there's very few instructions, so it's math on small numbers. But when they're actually running, they all converge right in the center above seconds. And an interesting thing happens there. You can see red goes from sort of metastable up to 1.5. Well, red was the HT sibling of blue, and blue comes down to meet it. So what happened was we started running something on an HT sibling, and red started running up at 1.5 instructions per cycle, but then we pulled blue down. So effectively, since we're running on HT siblings, it's not just how fast you're running, it's how much you slowed down the guy you're sharing the CPU with. Importantly, at this point, we're now running a lower IPC than the E cores. And so this tells you from a scheduler point of view, E cores are better than P cores when the HT siblings are busy. Okay, and that's an important observation. I should mention, I'm not going to get too much into the scheduler stuff. There is a scheduler micro conference tomorrow afternoon, and Ricardo and I will be talking about the scheduler aspect of this. We're mostly just focusing on the tool here. All right. This is IPC. Again, forgive the noise, but you can see it around 62.5. Every quarter second, we have 62.5 interrupts per CPU. What this basically tells you is that tickless idle is working, okay? So remember the pyramid. Right in the center, we're using all CPUs. We have very few interrupts on all of these idle E cores, but in the middle, when they're busy, everybody's ticking along at 250 hertz in this case. So 125 divided by 2 is what you see here, because we're measuring on a quarter cycle interval. It's sanity check, and if something's wrong, you'd see it there. Another thing you notice is that you have more interrupts on P core 1, which may be interesting. Okay, so this is tracking temperature. So in trying to figure out why we have that change in frequency, it might be interesting to know that there's a temperature limit. And the answer is no, we're under 80 C, which is perfectly A-OK. Though we do see things cool off quite a bit on that notch on the right-hand side, don't we? Tracking volts. This is interesting because on this particular chip, what it basically says is all the voltages are the same, okay? They're tied together. Now, this is not the same on every chip, but on this particular one, even the voltage of the idle CPUs is high. In this case, I don't know, 1.15 when they're idle, and their voltage is not lowering. So that's an interesting observation from an energy point of view. So talking about energy, everybody likes to think about power in terms of watts. This is a plot from the built-in energy meter, which we convert to power. And this explains finally what's happening with the big notch on the right-hand side. So here we're plotting package is blue, the entire SoC. There's a subset of that, which is IA, which is basically the cores, and depending on the chip, sometimes they're caches. And then yellow is the difference between those two. That's not actually measured, it's just one of those minus the other one, which is interesting that it's a constant on this chip. Graphics is reported as 0. I forget if this is, I think it's actually non-zero, but it's so small you can't see it. In this experiment, I'm not using graphics. And so what you see is, well, the y-axis is power, and this is a 15-watt TDP part. So at the pinnacle of this experiment, we're running at around 50 watts. And it's hard to run at 50 watts in a 15-watt package for a long time. And so the hardware basically corrects itself after it, you know, it gives itself some rope, and then it says, that's it. And it had to lower the frequency to maintain its average power budget. So it's runtime average power limiting is what caused that notch. Okay, now looking at this more from sort of a Linux and a work point of view, this is not a plot of processors. The key here, blue, is actually, these are thread numbers. Remember, we forked 12 threads, and maybe in the beginning when I had that FIFO chart, these are the same threads. There's 12 of them. They're called get CPU, because that's all this thread does, is continuously ask where it's running, which makes it very good at knowing where it is running. And you can see that thread 1 ran on CPU 0 basically its entire life, okay? And its HT sibling is CPU 1, CPU 2 is the next P core, and its HT sibling is CPU 3, and then you have the 8E cores. The 8E cores did about the same amount of work. And you can see, remember the top of that pyramid, you can see CPU 3 was what held something for 3-time quantums, and CPU 1 is the one that held something for 1-time quantum. And you can actually see which thread it was. In this case, it wasn't CPU 0, it wasn't get CPU thread 1. He had exited by, he was on CPU 0 the whole time. But this last guy ran on CPU 1, a little bit on CPU 3, and then migrated. And so that begs the question of, okay, where did what run? This is actually, from a scheduler point of view, this is where things get interesting. Most of that stuff was hardware stuff. So same key on the right-hand side, blue is the first thread. And so he starts running on the far left side, and he happened to run on CPU 1, which for sort of random where you wake up, because he's a new task. And that's the HT sibling for CPU 0, which is the bottom row. Okay, now there's just a dot there, and immediately the scheduler pulled him onto CPU 0. Why is that? Well, it's because as of this was run in 5.19, and it doesn't have Ricardo's latest patch to not do that. So we treat CPU 0 as a higher priority than CPU 1, and we pull from 1 to 0. Okay, and then he basically stayed there. Why does he leave right at around 10 seconds? Well, this picture is reported just by Yogini, completely in user space. So it's self-reported, where am I, where am I, where am I? You don't see, if you run a kernel shark, you'll see K-software QDs, you'll see any other activity in the system. Basically, he got kicked off of CPU 0, load balanced onto CPU 1. CPU 0 was a short kernel thread, then for the reason I just described, he got pulled back onto 0 because we're pretending it's higher priority. Another interesting one might be the red guy who started on CPU 4, which is an E core. The P core very quickly pulled him down in the idle load balancer onto CPU 2. You can see he got popped off the CPU a couple times. So one time he's way up on CPU 10. What's up with that? And the answer is, well, he got pulled onto CPU 3 when a K thread ran on CPU 2, but there was more than one thread. And so we now have multiple threads on an HT sibling. And in that case, the E core can run him faster. The E core idle load balancer says, hey, I can help with that. And he pulled that guy up to CPU 10. In the meantime, CPU 2 went idle again, and he says, hey, but I'm faster than you, as he pulled him all the way back to CPU 2. Does that make sense? Okay, you can draw this in a couple of different ways. You can have lines connecting it. This is actually just a scatter plot. Let's see, is there anything interesting? And then so more of the same. You can see how the this shape is basically just from the loop inside the scheduler where we just pull onto the next CPU. There's nothing magic about that, and it could very well be a different shape. The important thing is really the number of migrations. I mean, for this test, there's 12 threads and 12 CPUs. The more you're migrating, that's tax, right? You don't want to do these migrations. And here there's about 50. It's about 50 migrations. And I think after a small patch that we have to this, we can even get rid of those. Makes this picture a little less interesting, but less overhead. All right, so let's talk a little bit about the tool itself. Julia.
So is this small patch going to affect all the kernel or just the Alder Lake stuff?
Oh, the patch that I referred to, Ricardo
The ones that
sent-
will reduce the migrations.
Yeah, that migration will help in ITMT. I think just when you're ITMT. ITMT is how the kernel runs on a hybrid Intel processor today. So yeah, so I'll need a slide that says instead of 5.16, it will be 6.1 or whatever that patch gets into, and it will be a little cleaner. Honestly, on an interactive system, you probably won't notice, but on some things do notice 50 context switches. And in general, there's actually more complicated, since you asked, there's other cases where, like this red guy, and you moved here, and then you moved, it's not just a simple case. It can actually prevent some more complicated things and you really have to scratch your head and figure out why the heck did he end up there, and it eliminates those and sort of cleans things up. So I'm actually pretty optimistic about that change. Okay, so Mom and Apple Pie generate well understood workloads. We'll talk about the workloads in a second. To challenge the scheduler, power management and performance, and be easy to observe. So we just went through some of the things. We observed quite a lot with this tool. And we can observe it sort of from a bottom line point of view, performance and power, and you could even divide them and turn that into efficiency and battery life. Since the tests are simple, I'm hopeful that we can use this for regression tests to assure that we don't go backwards, which is something as probably most people in this room are aware is a constant risk. And so Mom and Apple Pie, make it easy to install, run, share, understand, compare, and extend. Extend is something I'm very interested in ideas on extending. I think it's very easy to install right now. It's a tar file, and you run the program and save it to a TSV file. I import that into Google, what is it? Google Drive, what's the spreadsheet thing? I forgot what Google calls it. Google Sheets, yeah, Google Sheets. And, you know, I guess this is a point of a success from a tool that you use it so much you no longer know what it's called. It's just there, right? So thank you, Google. You know, it's laid out as TSV, you drag and drop and boom, the thing appears. In fact, so what I just went through, it ran in 22 seconds. I saved it. It probably took, you know, a minute to upload it into the thing, and then a couple of minutes to create the slides. It probably took me more time to change the font in this presentation to a subtle shade of green than it actually did to create those graphs. Okay, so for each worker in Yogini, you can say what workload type you are. Get CPU is all I've told you about before. You can have any number of threads. Waveforms, which we'll talk about in a second. When to start and stop. You can affinitize threads and so forth. So to do this, first thing Yogini needs to do is to say, how fast is the hardware that I'm running on? Let's see, I start at 12, I have till 12:40. Okay, we're coming up on halfway, right? Okay. We'll start a system monitor. The system monitor is what gave us all that stuff about what's your frequency and that kind of stuff. It's basically, it leverages a lot of the stuff I wrote for turbostat. I don't know if you run a tool I wrote that's in the kernel tree called turbostat, does quite a bit of the system monitor stuff already. Yogini sort of has the next generation of that. It's a little more clever because it's newer, or I'm older. Then you run the work and output the results. So calibration, the rate in Yogini is in terms of percentages, and so Yogini has to find out what is 100%. So it will go off and it will run a loop and say, great, that is 100% because nothing else was running, and I'm just going to declare what 100% is for this workload. You can skip that calibration by remembering the calibration from previously, otherwise it will calibrate before it will run a test. The rate, the simplest thing is to run at 100% in this case, for 4 times 10 seconds intervals. This is actually a real Yogini minus W rate 100. That's all you need to do. There can be a start and a stop, okay? So this is what we did for that FIFO, right? As a script that created those threads that started and stopped at different times, ran 100%. It's this. Very interesting, often are periodic workloads. You can do that with a duty cycle. Here it's a duty cycle of 100%. And you can run at a rate. This is actually sort of important, a rate of work. So you've anointed something to be 100%, so you can anoint something to be 42%. And well, what is 42%? And yeah, and of course you can duty cycle that, right? Which isn't unrealistic, actually. There's some things that behave this way. And so how do you create that 42%? Well, from a processor's point of view, you're either running or you're not running. And when you're running at a certain frequency. I mean, if you zoom in far enough, but if you take a step back and you combine running with sleeping, that's what gives you your 42%. It turns it into utilization. So what Yogini does is it divides time, in this case, into intervals. The default is 16 milliseconds. And so 0 to 1 is 16 milliseconds. And it might say, oh, I'm going to run 42%. How much work in 16 milliseconds should I get done in 16 milliseconds? It runs that amount of work and it has no idea if it's going to finish that work or not. Now, in this case, since we've anointed it to be 42%, we know if we're running at the same speed as when we calibrate 100%, we're going to finish in 42% of the time. And then we see that we've got that work done. We sleep for the rest of the interval. Okay? And so you can set any percent. Also, say the processor were running slow because it were heavily loaded due to other processors or temperature or what have you. The tool doesn't care. It just says at this amount of time, I want to get this amount of work done. And if I get it done, great. If I finish early, great. If I don't, I get to the next interval and I just sort of start over again and say, well, what do I do in this interval? Okay, so the tool actually doesn't know about utilization. Utilization is a free variable. Work is a controlling variable. And that's an important concept. Okay, so how do you do something like this? We'll call this a ramp. And the answer is the function says, well, in this interval, my function is a ramp, and on the ramp, I should get 42% amount of work, and here I should get 50% work, and it just asks for more work, and it does 100%, and the only thing that varies is how early you finish, okay? So there's actually all kinds of crazy workloads. I even have a sine wave in there. I don't know. A ramp is the one that we use the most, but we can add in all kinds of crazy functions for work shapes. And so I talked about work and utilization. They're two different things, and it's very important to distinguish them. System monitor, I showed you graphs for most of these already. There's a couple of more. I didn't show run queue because in that experiment, nothing was in the run queue. Pretty boring graph, but from a scheduler point of view, run queue is pretty interesting. Oh, and the monitor, it runs every quarter second, but you can set it to whatever you want. Sometimes you want it fast, sometimes you want it slow for different reasons. Or you can turn it off completely. The way the monitor works is we create a monitor thread which which then forks off for, I don't know what, or will you IOU ring maybe someday. Thank you, Josh. Creates a bunch of other threads which all park onto a CPU so that it uses semaphore so that they can all take their statistics at the same time or very close to the same time. That's the reason it's done. And this is an area where it's actually smarter than turbostat. It's important to know when they're done, so the semaphore when they're done, so that you don't have a straggler and that your statistics are sort of lined up. The graphs work much better when the times are all the same or close. Okay, so if you just type in Yogini, it will monitor the system for 10 seconds and spit out the results of the system monitor because you haven't given it a workload. One thing that's useful is you can fork any program with Yogini, like, time my program, Yogini my program. And it will do this measurement of this entire system while that program is running. That program, however, does not include the built-in where am I and how much work did I get done unless that program happens to do that for you. It's not a built-in workload, that's a forked program. This last example, like WAVX, so there's a built-in AVX workload, and that will do that. So it'll do an AVX loop, and like the get CPU loop, every now and then it breaks out and says, okay, it's been this many loops, where am I and how much work have I got done, and so that we can track that over time at the end. And you can skip the monitor altogether. If you just wanted to run, say, AVX, you could just turn the monitor off. Sometimes that's useful. Okay, library of built-in workloads. Get CPU, as I described. RDTSC, all it does says, what time is it, what time is it, what time is it? Pause and tpause are also other ways to do as little as possible. Sometimes those are very interesting, particularly when mixed with other workloads. Particularly when you want the scheduler to say, be smart enough to put a pause loop next to a compute loop on the same CPU so that one runs faster, for example. RegAVX and RegVNNI, AVX2 are, they're register only, so there's no working set. Row2 SSC is streaming SIMD extension. I forget what SSC stands for. It's basically math with XMM registers. AVX is YMM. AVX512. .prod is basically a VNNI, so that's an AI dot product, but without the AI instructions. And then mem and memcopy, one's the Linux kernel memcopy loop, and the other's libc. So the reason they're in three groups is because the first row has no working set size. The second row does. And this is important because the working set size can completely change what that system, what that loop, first of all, what its score is, right? It can run much faster in cache than it can if it explodes the cache. So it's important to know when you run it, when you're comparing which, make sure you're comparing apples to apples. And B, you might want to say, I'm going to thrash the cache on this one or stay in the cache. The default is just the L1D cache, which would be the speed of light. And then the mem and memcopy, they default to the size of the L3. Oh, so this example in the bottom, here we have an AVX2 workload with a working set size of 256K and another thread, which is a mem workload with a working set size of 100 megabytes. Okay. Oh, yeah, question. Go ahead and read it for me.
Okay. 1, 2, okay. So how the heterogeneous schedule behave seems eCore couldn't run AVX/AMX.
I think the question was something about eCores running AVX.
That's right. So seems eCore couldn't run AVX/AMX. How the heterogeneous schedule behave?
Okay, so first of all, I should mention on the first slide, I usually, when I show the Intel hybrid architecture, I use the tagline, all CPUs run the exact same ISA. So you have P cores and you have E cores. All of them either run AVX or they do not. All of them either run VNNI or they do not. So Intel's products are homogeneous ISA or all the same ISA. So what Yogini does when it starts, it might be compiled, say, with AVX512, And then if you run it on an Alder Lake, it's going to, I don't have AVX 512s. When you try to run it, it'll just say, I can't run AVX 512. So hopefully that answers the question.
There's a follow-up. The person sent a link, so it's going to be hard for me to kind of click on that. But when Intel launched the 12th generation range back in November, okay, we were told
Could
that.
you do the mic? Maybe just take off your mask. I can't really understand you.
No problem. All right.
Okay.
So when Intel launched its 12th generation range back in November, we were told that AVX 512 wasn't enabled. Most of the tech press accepted that. Intel said it wasn't enabled due to the inclusion of two different architectures. The E-cores didn't support it, even if the P-cores did.
Okay, so this is tangential to what we're talking about today, so I won't go into it, but it is true that there are SKUs of Alder Lake where if you turn off the E-cores, you can run AVX 512, and Yogini would happily run AVX 512 on those if you should have one. I don't have one. Okay. Okay, I better move along. Okay. Worker threads, we already talked every 16 milliseconds. Oh yes, it's important to know that the worker threads are, they're self-reporting where they are running, and they're self-reporting how much work they got done. The first one they're an expert in, since they're doing the work. The second one, you know, it is possible to switch somebody there and back and him to say, I never knew that I was running somewhere else. Very difficult to fool the get CPU loop, since all it does is say, where am I? Okay, so we'll quickly go through the second example. Okay, this is a different CPU. This one has one P-core with no HT and 4 E-cores. And in this particular one, we're running an EAS prototype that Ricardo built, I think, a long time ago. And the E-cores are more efficient than the P-cores. So what we want to do is a ramp down, okay? So we're going to do a single thread. He's going to start at 100% and then ramp down to, say, 1%. And we would expect that at 100%, he won't fit on the E-core. He'll run on the P-core, because that's where he can fit. Right, that's how EAS works. And then when he's small enough, we should see him migrate to the efficient CPU when his demand is small enough. And that's indeed what we see. So what we see, this is a plot, not of utilization, but actually I went straight to work for time. You can see he started out actually on CPU 1, which in this case was an E-core, and he couldn't quite finish the work that he wanted to get done. Interestingly, it took 250 milliseconds for him to migrate to a P-core, and then he made up for it. He sort of spiked above the program, and then from there on out, he was on a smooth 100% of what he's asked for. Now, down in the middle, we sort of went metastable, right? We were doing some work on CPU 0, and we were doing some work on CPU 4. In this case, CPU 4 is the P-core. Sorry, the numbering is backwards on this CPU. Yeah, so the answer is it basically worked, but not really that great, honestly. And so if you look a little more closer, and in this case, we'll show the % busy utilization curve after, boy, that looks very strange on the middle and the right. And you can see that, yeah, we're keeping, let's see. We're keeping two CPUs busy for when we're jumping back and forth. And the other thing is we don't really see the E-core ramp down, okay, in busyness, okay? Now, why would that be? 1 minute? Okay.
No, sorry. There's another question online. I'm sorry.
Okay, let me finish explaining this picture.
Yeah.
Okay, and the answer is because the frequency ramps down. Okay, so if you're doing less and less work and your frequency goes down and down, your utilization stays the same, right? Okay, and you can also see here the similar thing with the orange didn't get smaller here either, and that's because we were at max frequency and our utilization went down, but then the utilization stays the same and the frequency goes down. Okay, so what does this mean for power? And in this case, we see a significant drop in power when we actually started spending most of our time on the more efficient CPU, which is the goal. And I think I just said that. Okay, so in addition to the workloads that I've built into the tool already. I'd be interested to know if there's other interesting ones. Regression test scenarios where we can see that, say, for example, in that ramp down thing, we can measure the total power, we can measure the efficiency, and we can run that before and after kernel change to see if we made things more efficient or less efficient. I'm not really a whiz at tools, but I just output this TSV and import it into Google Sheets. And that works for me, but maybe there's a more clever way to do it. Ricardo became impatient with that and has his own scripts in R or something that I don't understand, but they're pretty cool. They're pretty. And what's the best way to distribute? I do turbostat on the kernel tree. I don't know if that's the best model, but maybe there's that or better. I'm open to input. All right, why don't we start with a question online?
Yeah. Okay, so is Yogini more of a workload generator or workload monitor? That's question number one. And then question number two, okay, annoying question. For synthetic workload generation scheduler, people themselves use RT app. What was RT app looked at? Okay,
The first question was something about being a workload generator and a monitor. And
one or the other.
am I one or am I the other?
Are you generator or monitor?
Yes, so that's the whole idea, is to integrate those together. Yeah, so Yogini, you type it in, it's really quite easy. So I have a bunch of scripts around it. And yeah, it's a workload generator and monitor built together. That's the idea, was to integrate those to make it simple. I'm sorry, I've lost track of what the second question was. RT app, something about RT
That's
app?
right. So synthetic workload generation scheduler, people sometimes use RT app. Was RT
Yeah.
app looked at?
Yeah, I'm not an expert RT app. We've used RT app, but yeah, I really don't have much to say about RT app. So I mean, we're not replacing kernel shark. We're not replacing tracing. We're not replacing perf. We use some of those features here. The idea here is to integrate them to make them easy to use.
All right. There's another question. Would Yogini welcome other architectures such as ARM or RISC-V?
I knew I'd get that question. So in fact, I have to admit, I haven't even run it on an AMD system at this point. So I haven't, I work for Intel and all the computers in my lab are Intel. So that's what it runs on. But I have no doubt that the day I release it, somebody will say, here's the patch to make it work on AMD. And then, yeah, there's no reason that it couldn't run on ARM. The built-in workloads are actually, most of them are in C. And the directives are things like, hey, use AVX 512. Well, that's not going to work very well on ARM. So it would probably say, hey, use whatever ARM uses. So that same C code could probably compile there. Any other questions? Did I come in under budget?
Yeah, you are.
Awesome. Okay, thanks very much.
All right.
Okay, so thank you. So my name is Julia Lawal. I'm presenting OS scheduling with Nest. So I'm a researcher at INRIA, and this work was previously presented most of this work was presented previously at EUROSYS, which is a research conference. So I wanted to present it here, maybe not necessarily to say this should go into the kernel, but maybe we can think about the issues that we're talking about in this talk, which is the relationship between scheduling and core frequencies. So I would also like to point out that the second author is sitting here in the audience, so you're welcome to discuss this work with her as well. Okay, so I'll start out with just what is scheduling. So the goal of a task scheduler is to place tasks on cores when there are when a task is forked or wakes up, or when there's a need for load balancing. And then a task scheduler also, when a core has nothing to do at the moment, it figures out which of the tasks on the core's run queue should run. So we're actually only interested in the first of these aspects in this talk. So the challenge that we're going to be interested in is how can we place tasks on cores in a way that synergizes with the features of the hardware. So a very simple feature of the hardware is that a core only does one thing at a time. So this leads to the process, feature of, this leads to the property of work conservation, which is that since a core can only do one thing at a time, there's no point to put give several tasks to a core, because it's not going to do work on them if it happens that some other equally useful cores are idle at the moment. It would be better to put it on idle ones than on the ones that are already doing something. So here we have a little example. We have a teeny tiny machine that has only 4 cores. 2 of the cores are occupied with some tasks, and we have some task T3 which comes along. So where would we like to put it? And clearly we might like to put it on core 1 or core 3, because then the task will be able to start running immediately, won't have to wait for task 1 or task 2 to complete. So that's all pretty obvious. So we're actually interested in another feature, which is called dynamic voltage and frequency scaling, DVFS. So basically the cores can run at different frequencies, and we have a trade-off. Higher frequencies allow the application to run faster. On the other hand, they generate more heat and they consume more energy, and lower frequencies cause the application to run slower. However, in principle, they save energy and can generate less heat. We have this trade-off. Basically, the principle, which is respected by Intel servers and AMD servers, which are the ones that we have looked at primarily, more activity on a core results in a higher frequency. So this is implemented in some cases by the operating system, which may decide what frequency should be used based on recent activity and expected future activity. And it may also be decided by the hardware itself, which observes there are a lot of things have been happening on a certain core, which causes the frequency of the core to go up. There's another feature which is called the turbo frequencies. Turbo frequencies, so the machine has some nominal frequency. The turbo frequencies are some higher frequencies that can be used. But actually we saw this already in Len's talk. On Intel machines, the basic problem is if you run at these higher frequencies, your machine is going to get too hot and it will not be able to cool itself down. And so the machine deals with this problem in some way. So on Intel machines, there's only a restricted number of cores that can run at certain turbo frequencies. So the highest turbo frequency perhaps is only if you have up to 2 active cores can you use that turbo frequency. AMD machines seem to have a different behavior that I've looked at a little bit, but not in great detail. So then we can think about DVFS and how it relates to scheduling. So we have the same setup we had before. We have our 4 cores, 2 of them occupied, and we have a new task T3 that shows up. And so we can ask ourselves, on what core should we put T3? And based on the information available, we have the same answer. 2 of those cores are empty, and so those cores would be a good choice. But if we know something extra, which is that recently the scenario actually looked like this, then it could be a good choice actually to put T3 on core 1 because T1 has, T0, task T0 has somehow warmed up that core. There's been a lot of activity on that core. Maybe it's running already at a high frequency, and then T3 will benefit from that high frequency. And also, if we don't put T3 on core 1, but rather put it on core 3, then the hardware may think that there are actually 4 active cores, and that may cause the highest turbo frequency that's reachable to be lower than if it sees only 3 active cores. So this comes to the NES scheduler. So the idea of the NES scheduler is to take all these different issues that I've been discussing into account. So there are basically 2 ideas. The first idea is to reuse cores. So if we can reuse cores, then we will have fewer cores that are being used. And on the one hand, they will seem to be more active, so they will get a higher frequency. And also we will work better with the turbo constraints. If there's only, at least on Intel machines, if there are fewer cores being used, then we can go for higher frequencies. So for that, we maintain what we call a nest of recently used cores. So basically, nest is taking the ideas of CFS. CFS is when you wake something up, it's going to search over the entire machine or over the entire socket, and we're restricting the set of cores. We don't want the entire socket or the entire machine. We just want a restricted set of cores that have been used recently. And so if we only search over this restricted set, we are more likely to use a core that we have used recently. And so the second idea is to keep cores warm. So often what happens is that you run for a little while and then you pause and then you run a bit more. In the case of Nest, since we feel like we're going to be reusing cores, it seems like it might be a good idea to somehow artificially keep that core at a high frequency because it's going to be used soon. So for that, we do some spinning briefly when a core goes idle and in a goal of keeping up the frequency. So now I'll look at all of this in more detail. That was the main ideas of the talk we've seen already. So this is how CFS works. So the basic scheduler of the Linux kernel for general purpose tasks. So this application is running the configuration process of LLVM. Configuration for the compilation of LLVM. So I've actually studied configuration for various applications, including the Linux kernel. So they all behave in kind of the same way. They fork off a lot of little processes to see if different services are available on the machine. So what happens, so this graph is showing, we have time on the bottom, we have the cores on our machine with their various numbers on the y-axis, and the colors show the frequency. In general, red is the highest frequency and blue is the lowest frequency. That will be on, it will be that way on all of my graphs. So you see here we have sometimes, occasionally the highest frequency, but often lower frequencies. So what's going on? So basically, the way that CFX works is that when a task wakes up, it looks, there's a core which is called the target, which is often just the place where the core was, where the task was before. And then it looks at that core, sees if it's idle, and then it looks at the next one, the next one, the next one, the next one, next one, and wraps around. And so that's where we have this right angle, this everything is always an angle, it's always going upwards. Because you might start searching at this place, maybe the task was running there before, just one second, and then you'll look at the subsequent cores and then it always angles upwards. It's never going to notice that actually a core with a lower number is available and might be a good place to put this activity. So yes, we need, the box.
Thank you. Just have a question. When you're deciding on which next score to place, do you think about NUMA topology at all?
So this is not me, this is CFS. And if on a wake up, it's going to be just looking inside the same socket. This is a machine with 2 sockets, but each socket is quite large. It has 16 physical CPUs and thus 32 hyperthreads, and given the number of threads we have in this application, I mean, the size doesn't matter that much. Because there's plenty of room
The
available.
answer is yes, the load balancer pulls on the socket. But not here.
Not here. This is just wake ups and forks. There's no load balancing.
Yeah,
There's no
NUMA load
overloads
balancing
here.
doesn't happen at this time that she's talking about. It happens later.
Oh, okay. Yeah, the reason why I was asking was in some testing I did, I noticed that depending on how you place the processes with regards to the NUMA topology, you can achieve as high as like 30% power use difference. So that's why I was asking.
Yeah, sure,
Thank
but
you.
that's not what's going on here. Actually, to get the thing to fit better, maybe this is confusing for people who are very familiar with this architecture. I renumbered the cores so that the consecutive numbers are on the same socket. Oh, sorry. But basically what we see is we see a bunch of stuff and we see that they are spread out over about 7 cores, which is a lot. And one thing, it's not really completely apparent from this graph because of the granularity of the graph, but actually not very many things are actually, there's not much concurrency here. Very little is actually happening at the same time. And so this leads us to the idea of underload. So it's just a different perspective on the thing that I showed before. So our idea of underload is that what is the relationship between the amount of actual concurrency and the number of cores that are actually being used? So here's a completely artificial graph. We have this task that runs all the time, and then we have these other tasks that run for a shorter time. And it's easy to see that actually there's only 2 tasks that ever run at a time, but we're actually using 3 cores for them. So we say this is an underload of 1 because we could have collapsed all of these tasks onto just 2 cores. And so we can see for our configuration application that we saw before, there's lots of underload. We're using a lot more cores than we actually need at any given point in time. And so with Nest, where we're reusing cores instead of letting the tasks just drift off across the cores, we can actually obtain this. There's actually, we only ever need at most 2 cores at a time, and then they are running at the highest frequency. And this is just showing the beginning of the application, but for the complete process, we get a 16% performance improvement. So in terms of underload, we still have a little bit of underload. So the whole idea is that we need to keep the nests at a small size so that we are forced to reuse cores. So we're not perfect about that. It's something that's happening dynamically, and so it's hard to be perfect when you're making choices dynamically. But there's only 2 small cases of underload here, the red bars, and we don't have the huge underloads that we had before. Okay, so now I'm going to present the whole thing again in a bit more detail. So the main idea for reusing the cores is this idea of a primary nest. So as I mentioned before, we keep a small set of cores that have been used recently, and those are the ones we're going to search among, and then we can end up reusing cores instead of drifting across the machine. And given that we had the question about the NUMA nodes, actually we search across this primary nest first on the same NUMA node as the target, and then only fall back on the rest of the machine if it's necessary. So we complement the primary nest with what we call a reserve nest. So these are a few other cores that we might like to search over if we need to expand the primary nest. So that we might like to save in reserve if we need to decrease the primary nest. So cores that were in the primary nest but have not been used in a while. So those would be good choices if we run out of space and need to add more. And they're also, if we run out of cores that are in all of these nests, we just fall back to normal CFS and like ask it for another core, and that one goes into the reserve nest. So this issue of the reserve nest it also goes back to something like Len was saying. Sometimes we need another core because some K worker has drifted by on the cores that we are interested in, and so we need an extra one. But just because of this little tiny K worker, that doesn't mean that we want to put that core in the primary nest, because being in the primary nest says this is like the working set in terms of cores of the application. And so the whole challenge is, of course, to make these nests be the right size so that we get the reuse that we want. So here's a running example. Again, we have the green, which is the primary nest, the blue, which is the reserve nest. We have this situation, we have some task that wakes up. And so first we look in the primary nest to see if we can find a core for it. Of course, in this case, we can't, so that fails. And then we look in the reserve nest to see if we can find a core for it, and we can't again because they're all filled up. And so we go back to CFS and we ask, sorry, as I just, this is the thing I mentioned about the sockets. And so we go back to CFS and ask for a core. That's going to be this one here. And it's going to go into the reserve nest first. So some time goes by, that task went to sleep, and now there'll be a fork or a wake up or whatever. Now we have a new task we need to place. And first we look in the primary nest, and the primary nest is all filled. Then we look in the reserve nest, and this time we find something. And the fact that we have used this core twice is our heuristic to say, okay, this is an important core for our application, and so it's actually going to get moved into the primary nest, so it turns green. Of course, we don't want the primary nest to just grow and grow forever, because then we'll just go back to the CFS situation where we're searching over more cores than are really necessary. And so then we have some kind of garbage collection for these cores as well. So the primary nest, if a core in the primary nest is moved back to the reserve nest, if a task terminates on the primary core, then we figure, okay, we don't need this core anymore. It goes to reserve nest so it can come easily back, but we think for the moment we don't need it. And if a task goes to sleep, we keep it in the primary nest for a couple of ticks, but then after a while we say, okay, we can go to the reserve nest as well, because it might not wake up for a long time. So that was the idea of reuse. We have a small nest in which we search for things.
Do any of the cores ever drop completely out of all the reserve nests, or?
Yeah, okay, so that's a good question. I didn't go into this detail, but actually the reserve nest has a limited size, and when you've used up that size, those cores just disappear. Yes?
Something I have. Now you distracted me. I forgot what I was going to ask. But one other question is spinning while waiting for keep the CPU busy seems like you're fixing the symptom than the cause, right? It almost seems like you should need to make DVFS smarter than trying to give it the wrong signal to keep it at a higher frequency, right?
Yes, it's a possible idea, yeah.
And the other question was, I'm guessing you'll get to this later, how much power savings did you see? Kind of curious. And the other part is, we have a similar situation we notice in Android and mobile ARM CPUs where we see things in a sense kind of spread out too much. We'd like to see if there's any benefit in bringing them all together in fewer cores. But we haven't had any strong data yet to show it's going to be helpful, because a lot of this also depends on the particular CPU you're testing on. Some CPUs don't like being auto idle. Some handle it pretty well. Your DVFS graphs matter a lot. So I'm kind of curious how this all kind of falls into place.
Yeah, so when I get to the end of the talk, we might like to discuss that again, or I'll say some things about that. So he asked about spinning. So this is just the idea that we, when a nest task leaves the core, we spin for a little while. We cause the idle process to spin for a little while. It's supposed to be long enough to keep the frequency high for the next task, but not too long, because if you keep it spinning too long, then it will interfere with the ability of other cores to enter their highest turbo mode. So we don't want to do that. So it's just a heuristic of a couple of ticks that it spins. So there are some more issues about, sorry, how much time do I have left?
25 minutes. There's a question online.
Oh, sure.
Yeah, okay. Yep. We have a better tool to manage DVFS in the scheduler now until util clamp, it requires schedutil's CPU frag governor. By setting uclamp min to a specific value, you can bias frequency selection to honor this value.
Yeah, I'm not sure to fully understand the question. Maybe someone else.
Do you wanna?
Okay, there is now an interface, a user space interface you can actually use to specify you want to run basically at a DVFS point. So you can already influence directly the DVFS choices from user space. So I guess the question is why not using that interface instead of basically trying to achieve the same via the scheduling?
By spinning?
Yeah, by spinning, yeah. I think that's the way I understood the
Yeah,
question.
I'm not sure. So that's
An additional comment that was just made. It's an observation rather than a question.
okay. I mean, I would just observe that the spinning in practice is useful when we're talking about several microseconds long. I don't know if interaction with user space makes a lot of sense in that context. But I can look into it or look at the person who's discussed with the person who's asking a question later or something like that. So we have a couple of other heuristics that allow us to better keep track of the size of the mask that we want. One of them is the idea of a task becoming attached. This actually goes back again to the observation of Len about the K worker showing up and then the task has to move off to the side. We would rather, like, the way CFS is focused always on the previous core where the task was. Yes?
There's another question online. If I understand it correctly, is the reserve primary nest global? If yes, would there be any overhead when switching between nests?
At the moment, the nests are global. We're considering making the nests more local to individual applications. I'm not sure to understand how there would be an overhead between switching between nests.
Okay.
So sorry, to go back, a task is disturbed by some kind of daemon that shows up on their core. They get moved off to some other core. And if we kind of leave that as the focus point of that task, then our tasks are going to kind of drift around. As they get bothered by K workers, then they will kind of get focused on their new positions as opposed to their old positions that was in the original nest. And so we keep, instead of keeping just the one level of history as CFS does, we have 2 levels of history. And so that will tend to move the tasks back into the nest and kind of keep them on the same set of cores. We also have the idea of tasks that are impatient. So since for some kinds of applications, you might have several tasks which manage to always fit. They never run at the same time, and so they always manage to fit on the same core. That might change over time as they kind of drift. And so a task might discover that it is always getting interfered with by another task. In that case, the task becomes impatient, and then we just fall back directly to CFS because we feel like we need to get the primary nest to become as big as possible. We also, our goal is that nest should work well for the kinds of applications where it works well, kind of the things that have lots of scattered tasks that run for short periods of time. And that nest is not going to give us any benefit if we have, like, another common case is we have 64 cores, we have 64 threads, they just run all the time continuously. Just one second.
Sure.
So that's not, we're not going to get any benefit in that case. We don't want to get any overhead in that case either. And so we make, to address that, we make CFS be more aggressive about how it searches for cores, what we call wake up work conservation. And that way we can get the nest to be the proper size for the application as quickly as possible. Yes.
Yep. So per task has its own data flush previous tasks. $i, $D data is not good idea. That's, I guess, the cache, instruction cache and data cache. Not a good idea. Would a Nest scheduler focus on threads in one process, but still use CFS between the processes?
Might have to read that again slower.
Sorry, I really didn't understand it.
Let me repeat that. So per task has its own data. Flush previous tasks caches is not a good idea. Would Nest scheduler focus on threads in one process, but still use CFS between the processes?
The way that Nest works at the moment is you say, I'm running this application, I would like to run it with Nest, and the other applications just run with CFS in the normal way. So we change the different operations of the scheduler to look and see if it's using Nest, and then to use the Nest operations in that case. Otherwise, it just uses CFS.
All right, thanks.
I'm not sure if that answers the question, but there's another question behind you.
Oh.
It seems to me that this is where attached processes help, because they will tend to migrate processes back to cores they've just run on, which still have their data in cache. The question of whether multiple processes can become attached to one core at the same time and fight over their cache utilization is one I'm not clear about. That should probably be avoided if possible.
Yeah, so I didn't catch everything, but you said something about caches. So one could be concerned that because we're concentrating the executions on, we may have like multiple tasks which are sharing a single core, and so they will be flushing each other's caches as we go along. So we have done a lot of performance experiments, and we haven't seen that as a problem in practice, but of course, for certain applications, it could be a problem.
Oh, I got one. I think you want to run net perf round robin.
Okay.
Net perf round robin. So about a year ago, I did an experiment with Wake Up where, as that processor I was describing before with the P cores on the left, I said, well, why doesn't Wake Up always just search for one of those and sort of sort left? And it made a bunch of benchmarks go faster, but net perf got worse, okay? And the reason was because there was no cache locality, and these threads are waking up every 5 microseconds, right? And and they really wanted to have a hot cache.
Okay, so I'll try that, thank you.
So how does this algorithm take care of, preventing thermal hotspots? You're running them on the same cores all the time. So is there a risk of, heating up a part of the package, part of the chip by keeping the rest of them idle? I mean, do you want to, at some point in time, change what the nest was just to spread the heat around uniformly?
Okay, so I gave this talk at a energy conference, and they were concerned that I was going to be running things on 2 cores forever, and then that would destroy the machine, and it would be bad for, like the intrinsic cost of making a machine actually uses lots of energy as well. So I think that's the things what you're asking about. So indeed, we could, like Nest is also not perfect, and so the threads do actually drift off to the side sometimes, but one could introduce some kind of artificial drift every second or something like that that would address that issue. Yes?
If that's an issue, you should contact your hardware vendor.
Okay. Okay. So the last thing is, because Nest is reducing the number of cores that are considered, then it increases the chance that 2 cores that want to wake up tasks at the same time will actually choose the same core. And so we add a compare and swap on the choice of the core so that can't happen anymore. So that's something that can happen in CFS as well, but it happens more often in Nest. And so you get unexpected overloads. So now we have the evaluation. This is the underload for a whole bunch of different configuration things. This is the average underload over the entire execution. So we're often using 1, 2, 3, 4 cores too many. And then you can see in the red and yellow parts that Nest basically gets rid of that. For performance, we can see here this, now we have, in all of these slides with performance, we have 2 lines. We have the line for 0, and we have another red line here for 5%. So anything that's above The red line I consider to be an interesting performance improvement. Below 5%, it's hard to say. So basically, obviously, we do, our baseline is CFS Schedutil, and we do CFS performance, we do Nest with Schedutil and Nest with performance. So performance says that basically the frequency should be the nominal one at least. It might use the turbo frequencies if possible. Schedutil is an algorithm that tries to both give good performance when a lot of activity is happening and give energy savings when less activity is happening. So basically, not surprisingly, we get a performance improvement with performance, but we get a lot more performance improvement with Nest because we're making it possible to use the higher turbo frequencies. Performance doesn't do anything about the task placement, and so you still end up with 8 cores or so being used, and so you're limited to whatever it will do with that for the turbo frequencies. Yes, it's a question.
Yeah, this is very interesting. So I actually tried to do something similar to this with CFS. Okay. So in CFS, you have energy-aware scheduling, which you might be aware of, where they try to do something similar, but for different reasons. It's more like by packing tasks onto the little cores, you can keep the big cores idle and save power.
I see.
So unfortunately, that's very tangled up with ARM and config options and all this stuff. So I tried to take that code out and make it such that we could apply the same task packing to x86. I did not see that much improvement, but I'm curious if we can apply this to that and reuse some of that code. Yeah, maybe I didn't do the idle spinning stuff like that. That might make a big difference. And about the idle spinning, I think there is, like you said, the turbo frequency aspect, but there's also the aspect of I think the idle latency, like coming in and out of idle. I think the spinning can help there as well. So that,
yeah.
Yeah. So.
In this one, we're actually able to isolate where the performance benefit is coming from. Like, as in, do you know if it's because your cache locality is better, or for example, if you fix the frequency, if you remove the turbo frequencies as an option, do you still see performance benefit? Have you been able to isolate?
Yeah, so I haven't looked at that. I've only looked at the frequency. This is the frequency information. So we have these little groups of 4. We have little groups of 4, and so the first 2 are CFS, and the last 2 are Nest, and so you see more red. Remember, red is the highest frequency. For many of them, we have all red with Nest, and we have less red with CFS.
Okay.
So it'd be an interesting experiment, to suggest to get rid of the just force the machine to a fixed frequency and then see.
Or even remove turbo as an option. You can set an upper limit on the frequency.
Yeah.
Okay.
Thank you. Yes, so we have performance improvements, and here's where the how the frequencies cause those performance improvements. And for this particular case, which is kind of the ideal case for Nest, because we take lots of spread out processes and collapse them onto only 2 cores, we make the application much faster. We can actually save energy because we are just finishing faster. And actually, these machines that we use seem to have a high uncore frequency and use a lot of energy just for the uncore aspect. So by finishing faster, even though we run at a higher frequency, we can still save energy. So obviously, configuration of software is not the only thing people ever do. So we ran everything on the benchmarks of the Phoronix multi-core suite, which is about 200 applications that all do all different kinds of things. As I mentioned before, our goal is that Nest should not harm applications that are not getting any benefit from Nest. And so you see, actually, for many of them, we We just have no change, 159 out of the 200, but there are about 40 that actually do better. So these were not applications that were specifically chosen for Nest, they're just completely random applications. So all these numbers that we've seen so far are for Linux 5.9. So there's a caveat with all of what I've been talking about. So basically the idea of Nest is that Nest is trying to make things work better based on an understanding of how the operating system and the hardware work. So if the operating system and hardware don't do what we expect them to do, then Nest will still reorganize things in a certain way, but we won't necessarily get the improvements that we hoped for. So before happens that before Linux 5.9, before 5.11, Schedutil, so this is only concerns Schedutil is using this function here for changing the frequency. So Schedutil measures utilization and chooses a frequency that it thinks corresponds well to that utilization. So before 5.11, it was using this function. This function amounts to a suggestion. So it will say use 2 gigahertz or something like that, and maybe the hardware will do that, or maybe the hardware will do something else. Since 5.11, they use a different function for these machines that have a feature called HWP, and this actually forces the machine to run at a particular frequency unless that frequency violates the turbo constraints. So we can look at how Nest works out with that. This is a different application, which is H2. It's a part of the Da Capo benchmark suite for Java programs. So the graphs are a bit small, but you can basically see that these are, the colors are kind of purplish and so on. They're not blue, basically. So there's something above the lowest frequency. On the other hand, the threads, the tasks get really scattered out across the entire machine, so we don't achieve the highest turbo frequencies either. And that's with performance. With Schedutil, the frequencies are lower. They're not at the lowest point, but there's a lot of green in here, which is a fairly low frequency color. So this is 5.9, then we can run Nest, and Nest we see, so the thing to notice here is this is about 37 seconds, and this is 43 seconds. When we run Nest, we end up with 35 seconds, 36 seconds. So, I mean, for performance, there's not much difference because we were already using the turbo frequencies, but for Schedutil, we get a good benefit. The performance and Schedutil are about the same, but now we can use Schedutil, so we get lower frequencies being used at the times when we're not actually doing very much. So perhaps that's a benefit. But if we try, I also implemented Nest in 5.15. And then the results were quite disappointing. So performance, everything is quite fine. Performance is exactly what we were at before. This is a little bit faster, but it might not mean anything. On the other hand here, unfortunately, you can't see this very well, but now it's taking 70 seconds. And this up here, it's hard to see, but it is all blue. It's always at the lowest frequency. And that's pretty much how this application looks when you run it without Nest, with just CFS. It's also always at the lowest frequency. And so the problem is the way that Schedutil now works, this idea of Schedutil was always choosing quite a low frequency, but now that it's actually imposing the frequency, now the hardware doesn't have the choice to raise the frequency because more exciting things seem to be happening. So you can't really, unfortunately, you can't see it very well, but we are consolidating the core tasks on the cores in exactly the same way before. But the problem is that if you zoom in, you can see that there's still little gaps between the things that are happening. So you run for a little while. I mean, like Nest is going to take all that stuff and collapse it onto a single core, but it won't erase the gaps between actions. And so those gaps cause Schedutil to choose a low frequency. That's just the way the Schedutil algorithm works. And all of that spinning that we try to do has no impact because Schedutil is not taking what the idle task is doing into account. So in conclusion, we have introduced the Nest scheduler. The idea of it is to reuse cores and hopefully to try to keep cores warm, although we were not completely successful with that in the 5.15 case. We get performance improvements between like 10% and 2 times on applications that have kind of a, they're multi-core applications, but they're not like using the entire machine all the time. And we've tried a whole bunch of different kinds of machines for that, and we maintain the performance for applications that use the entire machine all the time. And as we showed on the previous slide, the impact of all of this depends on the actual power management strategy of the operating system and the hardware. If they it was designed to cooperate with how things worked in 5.9, but if more recent versions don't respect that, then we don't get all the benefit we hope for. And everything is publicly available, all the tools, everything to make the graphs and so on. Thank you.
All right, so there's an online question. Is Nest its own scheduler class with e.g. its own pick next task function, or does it use CFS with Nest hooks like changing select task RQ function or something else?
Sorry, what?
Or do you want to read it here?
Yeah, I can read it myself.
You can switch it over to.
Let me just read it from.
Yeah.
Is the Nest scheduler its own scheduler class? No, it's not the only. It's not its own scheduler class. I just modified the existing code.
Okay.
For what it's worth, I found it quite easy to modify the scheduler. It was no real problem. It didn't crash very much. It was fine. Okay. Are there other questions?
Raise your hand, you're going to get hit by one of those. You mentioned, I don't think we're working your program.
Need catch practice. Oh, you mentioned trouble with spinning in idle and schedule not picking that up as a load. Perhaps you could spin somewhere else, like kernel thread or something else.
Yeah, so I spent a lot of time on that, like 2 months or something like that, trying to get that to work. So there's like the sched idle task and sched idle class, and then in principle, it will only run when other tasks are not running. But there's some race conditions in the scheduler that can cause a sched idle task to run even if there is another real task waiting on the run queue. And then once it starts running, it will just keep running. It won't get preempted by the other one showing up. I think they basically show up at the same time and the scheduler picks the wrong one. And that has destructive impact on the performance. Okay, so, I mean, I read up like some documentation about sched idle, and it said mostly it should happen in this way or something. Mostly it should happen in a good way. So I didn't see like any kind of guarantee. It should never run when there's another process available. But I don't know what the status of what people want from sched idle, so I didn't report it as a bug.
Right, so there's 2 questions online. The first one is, would Nest scheduler decrease the semiconductor's life?
Yeah, so I think I answered that one already in the sense that I don't know if we use the same core for hundreds of hours, like Len says, we should just complain to the manufacturer.
Okay.
So.
The next question, could the Nest scheduler simply switch P-state policy instead of spinning? And there's a second part of this question, or that would keep the CPU at a high P-state without taking any compute power away from the other hyperthread, or would that break turbo modes?
Okay, so I think what the question is about the schedutel in the more recent version of Linux. And so I was also thinking about, in the last few weeks, about like, could I just pretend that I had run? I mean, in terms of schedutel, all we care about is the utilization. It's just a number. We could try to increase it. We don't even have to spin or do anything because schedutel is telling the hardware what to do. The hardware is out of the loop now. But I couldn't figure out a good way to do that. the idea of spinning is you should it's just like a little boost for a little amount of time and not to fill up the entire gap. So it seemed complex, but maybe I missed something. It could be done in a different way.
All right. So we're out of time, but
Sorry, okay. Or you could discuss
quickly because
afterwards.
we're sort of out of time.
Yeah, I'm sorry if I missed this part, but can the threads choose between being a nested thread and just completely dropping out of it? Like, are you able to change those states?
Yeah, nothing is planned for that at the moment, no.
Thank you.
Thank you.
So thank you.
Two. Hey.
2, 2, 2. So what you see level-wise should correspond to the room, okay? 2, 2, 2, 1, 2, 1, 2. Coming in, coming in, coming in. 1, 2. Yes? Perfect. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's nothing coming in on the stream to me, so we should be clean.
Is a chance for the Hyperledger community to come together as one community. Pulling together people face to face, we think is really important because when you see some of these words in an email, right, you're kind of not sure how to respond, sometimes what tone they mean, but when you've met them
So
face to
nothing coming
face.
to me at the moment. Yep.
You can hear it in their words, and you have that kind of level of trust, perhaps, with them. Suddenly, collaboration.
1, 2, 3, 4, 5.
The Hyperledger Global
6, 7, 8,
Forum is
9,
our
10.
annual event
Still seeing
for
nothing on
people.
the stream to me from you. You are muted.
Around the world who are using distributed ledger technology to find out information on how it's being used, how to use it, to meet the senior people across the entire
1, 2, 3,
spectrum
4,
of
5,
technology, of
6,
business
7, 8, 9,
leaders,
10.
of users who are
No
using
looping, no feedback, all good.
Working? Welcome back. Hopefully you had good lunch. So we're continuing our session, and the next presenter is Daniel, and he will talk about where we are heading next. Right.
So good afternoon, I'm Daniel, I work for Red Hat, and we will talk about a new subsystem that just happened to be merged in the kernel, which is RV. And so just a summary of what we discussed, I will briefly present what is RV and the reasons behind the idea of the patch set. And then after this initial idea and the research purpose that it was raised, right? It got some attention from the people that are trying to run Linux on safety critical systems, and that motivated the productization, let's say, of the research. And I'll explain a little bit of where are we now and the structure of the RV in the kernel, and putting emphasis on discussing what is next, what will come after. So RV, runtime verification, it's a lightweight but still rigorous formal method that is useful for the case where you have an actual system. Because instead of relying on building an entire model of something and try to verify the model as like statically, RV works by analyzing the trace of a real system. So in other words, like the dynamics is like, as the system runs, it generates events. And these events are analyzed against a well-defined description of the system, right? We can do some kinds of runtime verification. We can do online synchronous when the event of the system is analyzed synchronous to the system. So it blocks the system, analyze, and then let the system runs. It can be online asynchronous if like I write the event to a trace buffer and then analyze it in user space, but without blocking the system. Or we can do offline, like saving the trace file and then later analyzing it. And the current method that we have in kernel is online synchronous. So the analysis should produce a verdict saying if it's okay or not. And on online verification, we can also react to for example, a verdict that an event was not expected. And then you can react to this, take some actions. So having a look with a diagram that makes things easy. So in one side we have Linux, and the system as observing the system or generating events from the system that can be analyzed. And in the other side we have like the formal realm, where we have a formal description of the desired or undesired behavior. And then we connected these two things into a monitor. And the monitors analyze the glues the formal specification and the trace. And if things are okay, can you say, okay, everything's okay? Or if an event is not expected, it can react to an unexpected event. So why trying this formal, right? We can do this analysis informally. The reason why it's useful also to be formal, it's because it's precise and unambiguous. And when you're creating a formal specification of the system, you are trying to think about the way that you expect the system to run, and not exactly about the code. And you are not producing code, you are producing a formula, like using an automata or other ways to formalize the specification, like with TLA. And you can verify your reasoning. You can verify that formula using other approach, like checking if your reasoning has a deadlock or not. And the good thing about demonstrating as a behavior using a formalism is that it's easier to take results to another kinds of formalism that I will explain later in the case of the scheduling latency. And moreover, it helps to document the code. But we will get into these points over the presentation, and it will be more clear. So where are we from, right? The idea of using runtime verification, it was not the goal, it was a need. Because in my PhD research, my main goal was to demonstrate the bound for the scheduling latency. And And the idea was that I could provide evidences for the real-time academic community that Linux had abound. And to do this, I had to explain the system. I firstly tried to explain the system using natural language, like English. And my English is not that good, but even though that was not the problem, the problem was that it's ambiguous. It's not, you cannot clearly see like 2 + 2. And I also tried to find a way that would be meaningful for Linux developers to look at it and say, okay, I got the idea and I can understand it and I can check it. So, and the way I found, the formalism I found, it was the automata, and I was able to create a model of the preemption model of Linux. So I could model the preemption model of Linux using automata and generate this publication. It presents all the details. It was a very, very large system, like more than 9,000 states, but it was built on a set of small automatas. So it's possible to create large models from small models. And the formalism I used was automata. It is more known because of this graphical format. That's easier to understand. But this drawing here, it has a formal structure using sets. So I use that automata. That's the part that is helped to bring from one kind of formalism to the other, right? So I explained Linux using this formalism, and then translated it in a set of lemmas and did a theorem that explained the scheduling latency, and it was understood by the real-time community, and that was a goal. But as I was doing, so my goal was to provide evidences of the scheduling bound. But as I was doing this verification of the model, I ended up finding problems in the kernel and reporting problems in the kernel that my model described the system as it should. I firstly tried the model until the model started to produce meaningful results. But after a while, I started seeing that the model was correct and the kernel not. And I started reporting bugs. and as I was doing this, people were giving me feedback that my side product of the PhD could be more important than my real goal, that was the latency, which was, okay, if I could run this specification, any specification using a formal method in the kernel and could check if the kernel is behaving as expected, we could use it for multiple reasons, like testing or to provide other kinds of demonstration. And that motivated the development of this paper, that I tried to make an efficient way to transform like an automata into something that I could run and I could produce and do the monitoring and could produce some verdicts. And here's the paper with the details. The good thing was that running the automata in kernel was, because it's just an O of 1 operation, it was faster than tracing the system for a later analysis. So this is, here is just one example. So I have the system running as is, the more operations, the better. And I have the system tracing. And here was the system analyzing those traces in kernel running the automata. So the main idea here is that, okay, it gives some overhead to the system. These are extreme cases, right? But it adds some overhead, but the overhead is lower than tracing for later analysis. And we can conclude things like, okay, if I can do this efficiently, and we can run trace in production, we can also do analysis in production. And then while I was showing these proof of concepts, talking about proof of concepts, I ended up meeting the people that work with safety for critical systems in the ELISA working group at Linux Foundation. And then when I did this presentation at ELC 2019, and then people from Mobileye, Intel, and other people in the ELISA work group came to talk to me, because they say that there are some kinds of testing and documentation that we need to do to provide to certification authorities to certify that the system can run as a safety critical system. And the usage of formal methods was the top level. It was the one that provided more benefits. And the main, I'm not an expert on the safety analysis, right? But trying to summarize, it was a good thing to use the runtime verification with automata because it produced a documentation of the system using a formal expression. We can verify if the system is behaving as in the documentation, and we can actually run the documentation when we run the automata in kernel. So we don't have this step of translating the test into code, right? The documentation, or better, we don't have this step of translating documentation into code. The code and documentation are the same thing, just expressed one in a draw and another in the code. But they are both from the same source. And we can also have these monitors at runtime reacting to unexpected events as the safety critical system runs. So if something didn't run as expected, you can shut off the system and go in a fail safe mode. So, and that motivated, that gave me the motivation, that community gave me the motivation to pursue it, trying to productize this research, right? And another good point is that there are very strict rules that we need to follow to apply those things to safety critical systems. And the good thing about the RV with automata was that it was pure NC, straightforward code. And I was just using statically allocated memory, no loops, and so on. So it is the kind of code that is closer to the kind of code that people generally certify for safety critical system. And here is the talk where I was talking as this as a proof of concept. So while working with the people in ELISA, mainly Gabriele Paoloni, we started drawing the idea of how we can feed the runtime verification into the safety analysis that people need to do, right? So we start with the requirements of the system. These are the requirements that we need. And then we create the specification, do the analysis, and try to exercise this analysis. So we create a documentation using a formal format, using automata, and then we try to verify the system. So until the point where we get our requirements well defined or defined well enough so that the monitor can produce only real verdicts, like we start modeling a system or start modeling a specification, probably not in the correct way, right? And then we start refining it and understanding as the system runs, and we keep going to the circle. Okay, I modeled the system this way. The runtime verification say that there is a problem here. The problem is not the codes and the specification. So you go in a cycle until showing that your specification is reasonable or is good enough. So we use it to refine our specifications, like refine the reasoning and check the reasoning against the real system. And we can also monitor it as the system runs if necessary, if that's a critical enough operation that we need to constantly monitor. So RV can be used to document the kernel, and then we can show how the system should behave or not. And another point, if you see this presentation, it goes deeper into this safety analysis. Gabriele goes deeper here in this presentation, and he explains how we can use RV to break down, because the kernel is too big to be certified as a black box, or it's too hard to certify it as a black box. So the idea of this presentation, it shows that we can split the kernel into small pieces using runtime verification. We say this block should behave this way, this block should behave this way, and these small blocks can be certified as black box. And here's I think it was at Plumbers last year, where we explained how do we glue runtime verification with the safety analysis. And but the expert on this is Gabriele, it's not me. I'm just helping with the technical side. So where are we now? The good thing is that we are merged in part, right? When I submitted this presentation, it was under submission yet, but it happened to be merged for the 6.0. The idea was to present here the pad set, but as it's merged, I will present the things as they are in the kernel now. But the thing that was merged is just the initial part, and then later we talk about what is next. So trying to get some abstractions that you have here, right? Recalling that diagram, so we have this monitor that connects the model, the specification, with the instrumentation, and then we call this a monitor. A reactor is an action that can be taken when an unexpected event happens, right? And the monitors can be enabled at runtime, and each monitor can have its own reactor enabled. So I will try to share this video here. Just a second. I've tried before, it didn't run smooth, but let's try anyway. Come on, you can do it. So the interface, now the interface is stored inside the tracing subsystem. I stored it there because RV consumes trace, and these file abstractions that Steven has on the TraceFS, they are handy. Just showing here, the system is just regular mainline kernel 6.0. Come on, video. I was typing faster than that when I made the video. So here is the interface. We have the available monitors that show all the monitors that I have loaded in the system. Each monitor is that part of a little bit of automata and a little bit of instrumentation. Here we have these two monitors. And we have these reactors available. So we can do a print K, we can panic, or you can do no operation, which is the full case. This is the enable. It's like the set events in ftrace. So it says that there is no enabled monitor.
You see if there's a better contrast, if there's a contrast button for the on the board, is there a contrast?
I don't know. I'm not used to this laptop.
Oh, I see it. Hard to see.
Okay, I'll keep it running because it runs so slow that you do your operation, it will be still in the same page.
Switch. I'm trying. Let's see. I know there's speakers. There's brightness. Oh, that's brightness.
Yeah.
But is that? I don't. That's
Yeah, I think that's a different.
Did it make it? Well, that's just brightness, I think, right? So does it make it better or worse? Which bring it down here? Is that better or worse?
Yeah.
Oh.
That's this screen, not that screen.
Oh. Well, so it doesn't affect the output. Shoot. Yeah, it's too bad. I don't know which one would be contrast. Is anything, you know what sketch is that? Is this contrast? Oh, that's probably brightness. Yeah, that's brightness. Okay, I tried. Which one?
Go back to the video.
Okay.
It's on the.
On this?
This one?
On auto.
That's 1080p.
Well, this is going through BBB, right?
Yeah.
So I don't know, is that going to work? I don't know if it's going to hurt. If I, what? Reduce it to what? What's it at? So it's 720, so if I. Better or worse?
Try a higher resolution, right?
Well, the thing is, this is BBB, it might kill the server, I don't know.
Yeah, that's probably why it's running slow. It's because of the server.
Yeah, I might put it back to auto just because I tried. Because I have trouble reading that. Oh.
Come on, BBB. So here we have we have this monitoring is on and reacting is on. So if I run a monitor, it starts monitors. If we have a
a reaction, it will react. So here I'm saying echo WIP to enable monitor, so I'm enabling the monitor. And it says now it's enabled. It resembles ftrace on purpose. And let me try something. Okay, available events. So the monitors also create a set of events that we can observe via anything that can trace. For example, we can observe via perf or via ftrace. And so here I'm enabling all the events for the monitors. And if I see the trace, I swear I type faster than that. And see here are the events. I'm saying I'm in the preemptive, I have preemptive disable, no preemptive. I'm in no preemptive, preempt enable, no preempt. So you can follow the monitor as it runs. Okay, I'll try to just jump to the. Okay, I just jumped into each monitor has its own folder. And in this folder, I have some files that says the description, if I can enable it, and change the reactor. And here I can change the reactor, say from NOP to print K. So I've set print K as the reaction. And if I do the mask, I will see the reaction here. So there was a print K saying that this event was not expected. And I can panic the system as well. So another thing that is in the patch set is the monitor synthesis, which is, there's a tool called .2k, and it is used to translate a automata into a monitor that can run in the kernel. And so the monitor that the .2c creates, it uses a set of macros to expand the entire monitor code. So people doesn't need to re-implement the basic automata verification each time. And I use the C macros to make every monitor independent from one or the other. And the only thing left to do is the instrumentation part. This is the last video, right? I'll try to show how this actually works. I'll try just to move the video by hand instead of letting it play. So here I have the WIP.dot file. It's a dot file from GraphViz, and it has an automata, the specification. And here I will run the .2k program, saying that I want to translate this WIP into a monitor, and this monitor is a per CPU monitor. So each CPU have one monitor running, because the preemption disable is, this monitor uses preempt disable, which is a per CPU thing. So, oops, too much. So I've run the command, and it will create these files. So it creates a directory. Inside this directory, we have two files. And here it gives a checklist of how to integrate this monitor into the kernel. So this file is the .age, and it's a C representation of the automata. And it's a direct translation. There is a documentation in the kernel that explains this translation. And here is the monitor itself. It has some sections, and it tells what to do, but most of the part, the work is just is just changing these handlers or for the events, telling which trace point will handle these events. So I direct a trace point to a handler that will handle the event, throwing this event inside the runtime verification monitor that's created. It will be easier if the video just run, but it runs so slow that it's not helping. So the RV structure. We have this interface inside the tracing. And here we have the files that the rv.c here, it does the startup and the registration and control of monitors. It registers the monitors and give me that interface to enable and disable. And the RV reactor, it is the control of what reactor is running for each monitor. And we have like examples of reactors here. Each monitor has its own folder that has those two files, the monitor, the instrumentation part, and the automata part. And it's important to keep them separated because it's more clean, or it's more, let's say, it's easy to justify that this is a formal method if you keep the formula in one side and not embedded in the code. And then we have a set of headers that are responsible for the files that I use to register a monitor, and that serves to generate the code that analyzes the automata. So the person doing the monitor doesn't need to re-implement them. And also, when we do the safety analysis on the code, we can just do it in one code and not for each monitor. And here we have a set of tools, that is that .2c, that translate automata into code, and have some template files that are used to generate these monitors. And I also have here some sample monitors, the dot file, the automata, and they can be used as a starting point. Here I have another video that shows how to edit it. There are multiple ways to edit automata, but I better not play video anymore. And also, and as important as the code is that the current pet set has let's say, a nice set of documentation that explains all the idea, how I translate automata into the dot file into C code. So you can use that to understand the things that are there. And also for each monitor, there is an explanation of what the monitor does, the reasons behind it, and how to read it. So all those things, fortunately, were merged, but they are just the starting of this subsystem, if we can call it a subsystem. So, just a second. This is a monitor that has been that we developed together with the ELISA working group. It's hard to see here, but the idea is that we can follow all the operations that we can on a watchdog that brings to the system to have a watchdog armed. So one needs to open the watchdog device, need to start it, need the system, and ping it at least once to reach to the safe state. So for us to have a system, for us to have a watchdog as a safety monitor for the system, we need to follow these steps and keep running around this this state, which is considered the safe state. If the sequence of events is not provided correctly, we will not hit the safe state, and we cannot start the critical operation on the system. It was part of the initial implementation of the pet set, but and it is generic. It should work for any watchdog. But in the pet set, when I submitted it, I had the automata monitor and a set of options, and it was not clear for everybody what was the monitor and what were the options. And to avoid confusions, I took off the dispatch. which was a single patch, and I will send a patch set explaining this is part of the monitor. This is these are the options that enrich the monitor, and so things will be clear for reviewers to understand. It was my fault. I just had to make it more digestible. And the patch set included a user space tool that exercised the monitor. Another thing that if we check now, all the monitors, they doesn't have any way that we can feed it with options. So, for example, in the Watchdog monitor, I have an event that set a save timeout. And the save timeout has an argument that is, for example, 10 seconds or 1 second. I have no way to set these options for the monitors yet. And, but, questions? No? Okay. So the idea here is that as each monitor has a folder, I can have a file there with the options for each monitor, because monitors will have different options. And I'm not sure yet if I will have one file per option, or if I have a single file with a set of options and specify, okay, this option is an integer, this option is a char. And that's something that I still need to think and discuss with people. Okay.
Thank you. Yeah. About synchronization. First of all, for the monitor, how do you do locking? When it's per CPU, it's one thing. When it's global, it's maybe something else. And how do you guarantee that you don't impact the system or have a priority inversion or things like that in your monitor?
Okay, the monitor, it's monitoring an event of the system, right? In general, these events of the system already provide the synchronization with the other people that would use that event. For example, in the scheduler, the sched wake up and the sched switch, they are protected by the RQ lock. So generally, the system already provides you the locking mechanism that will provide the atomicity for the things that can run concurrently with that event.
Okay, so your state transition is sometimes protected by the color locks.
Yes.
Okay.
Most of the case. In the future, we might need to add this synchronization inside the monitor. But the way that is using macros like trace points. So you just need to change the macros and provide, like, instead of declare a per CPU monitor, you can say declare a per CPU monitor locked.
Yeah.
And then we can expand. But so far the atomicity is provided by the event that's being generated.
Same question about the reactors. So you have a printk reactor. Printk can have side effects when invoked. So do you invoke it from the color context, or you do a IRQ work to let it run somewhere else?
I'm calling from the colors context, but I'm using printk deferred because I cannot call printk yet in the.
Okay.
Yeah.
Thank you.
Yeah, good question. You went to the code straight. So yeah, we have these options. Another thing is that at this point, initially I have made everything as a module, and then I start integrating with the kernel. All these functions here, they were thought to be exported for other modules, so we can load monitors as modules. But to avoid problems in the initial implementation, I just didn't export it. So I can still have some time to think about it and to avoid problems to myself in the future. But it should be straightforward. These are the functions that I need to export, so I can have it as modules. One thing that people asked many times is that why not making these things with eBPF? And yes, it's also possible to have these monitors with eBPF. There are some pros and cons on having it in kernel and in eBPF. But one thing that I made clear is that I'm not creating tracing features or creating language. I'm a user of these technologies. And the more technologies we can have to use, and as long as we have people that justify that development, I will use it. I'm not a fanboy of any, let's say, language. So I have a tool that is .bpf that is like the .2k that translates monitor into C code. It translates into a BPF. The idea is almost the same. It uses libbpf and C, so I can reuse all those headers that I use in the in-kernel implementation. I just need to create some if-defs saying, okay, get per-CPU variable or get per-CPU map. I still didn't send it because it has a dependency on this. I wanted to first close one implementation in C and have it reviewed, and now I can try to edit and make those things use the same code base. And there's also other kinds of monitors that I'm using. And I'm using now, we are still developing. I work with ETH Zurich and the University of Copenhagen, to other monitors that do offline or online asynchronous, and I'm using Trace and BPF for that. So there will be space for everybody. And but the main motivation so far for these monitors is the usage on safety critical systems. And these safety critical systems, they have a set of rules that they need to follow to be qualified as a safe system, right? And the rules for the pure C code are already there, and they are well established, and the RV was developed somehow with that in mind, right? But still, we need to make an effort that is more in documentation part and reviewing the code part to try to qualify that C code for safety critical systems. I did it initially with that in mind, but there is still this work that needs to be done, and it might result in changes on the code or in the creation of another type of monitor that is qualified. And that's the work that I'm doing with the people in the ELISA working group, and Red Hat is supporting me on that. And finally, there is this this part of integrating. So this always started with the preemption model, but I'm still not proposing it, right? Because it will require some extra work in the instrumentation, and that WIP monitor, it reports a limitation of tracing preempted disable events. That's why it causes reaction. And I need to fix that problem before trying to integrate the preemption model for the preempt RT. and yes, part of my work now it will be trying to instruct people on how to create other monitors and do other monitors myself. And as I said, I'm creating mechanism for other types of formalism. The language is MPhoto that we can also use and expand RV, not only with automata, but including other ways to express formulas. So in this is more complex than automata, allow timings in the equations. It will be nice. And yeah, that's it. Sorry for the videos. It didn't work well. Questions?
So have you tried using, on your models, using a SAT solver or using the spin model checker to check, okay, in what I have modeled, I validated that when the kernel runs, it actually fits the description. And then from that description, can I explore all the possible state combinations and see if it matches some constraints?
Yes, you can do that. Like what I did for the preemption model is that I use a tool that's for the development of automata. And that tool that is Supremica, it's an academic tool. It already gave me some kinds of things that I could check. For example, I could check if there was a deadlocks inside the automata, and assuming that Linux works correctly, there should be no deadlocks on my automata. So there are tools for making that, but they are generally in the phase where you are developing the formalism, right? And for automata, I think it's most common and most simple way to formalize something. There are a lot of tools for that. But the other thing is that how can I take out the information from the automata that I'm running to see what were the visited states, how many times that the event happened. That thing is easy to be done on top of this current implementation, because I can just hook to the events generated by my automata and do the analysis on that. And that's why I'm exporting the, the results as trace points, because then we can connect them. And still, there is all these ideas to be developed there, and that's a good thing. Hey, Joe.
Hello? Yeah, so I was just curious, have you implemented like liveness checking and deadlock checking and all that kind of stuff?
So these things can be done in the automata with tools like Supremica.
Okay.
Yeah, that can be done in the development phase of the automata. And
yeah.
Do we need to re-implement those tools? Maybe, I don't know. But for the automata, there are those liveness and check if there are deadlocks, if there are live
but so you're saying that it doesn't make sense to check that at runtime? Or?
I think as you have the formal description, we are trying to check the formal description itself, right?
Yeah, that makes sense.
So you can do that in the development phase of the
tool
automata.
itself, yeah.
I did that for the preemption model during the.
Okay. And then the other question, I guess, is do you feel like trace points are sufficient to drive the model, or do you feel like, because I can envision like anybody who needs to use this stuff, they'll need to have the trace points, right, in the first place.
Yeah.
And so the question is like, how much detail can you expose through the trace point interface, and at what point will that be like, adding trace points just to
justify the monitor.
Yeah.
Yeah. So one limitation or one characteristic of runtime verification is that I can only verify what I can trace. If I cannot trace, I cannot verify that. That's just not the correct tool, right? So if you have a monitor that needs a trace point that doesn't exist, we can probably in C code, we can do it at runtime, using K-probes, more overhead, blah, 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 or trying to convince the maintainer to add trace points.
Yeah.
As long as the monitor justifies adding a trace point. But yes, we depend on trace points, or trace points or anything we can trace.
Yeah. Microphone? Yeah. I think you on the callbacks on the trace points, right?
Yes.
So you don't depend on whatever is exposed as ABI to user space. So, and there are trace points now in the scheduler that are callbacks only, and we can modify those as we wish, as we want. And they are haven't they been added for you actually? Those trace points?
Yeah, they are. I can hook.
They were added for people writing kernel modules to get like scheduler.
But we had that discussion at Plumbers in LA, I think.
Yeah.
And then I was presenting the model, and we discussed with Peter because of the deadline events that I proposed some years ago.
Yeah.
And he said, okay, as long as you don't export, you can add those events.
Exactly. So you can add those.
Yeah, but the good thing about these trace points or these things that you can export via trace is that many people depend on it nowadays. Like BPF is entirely built on top of that. So I'm just another user of this infrastructure.
So I think this would also be quite interesting, bringing it to user space with U-probes, or even better, like the user space dynamic trace points, where you can actually coordinate, you can verify the runnability with the kernel and applications working together.
Yeah.
I could see a lot of power there, especially with the user space dynamic trace points, because the user space, the developers, they specify the variables.
That's just translating a little bit. So now we can have trace points on user space, and you can also add a U-probe for quite a while. So you can create a single view of the system, integrating both user space with U-probes and user trace points, and the kernel with the kernel trace points, with a single view of how things should behave. Yes, that's an interesting use case, and that probably will be a user for these now user-defined trace points. That's why it's a good thing to depend on trace points, because many people depend on trace points already. trace points, trace events, and the function tracing, anything we can hook. Oh yeah, I think the time is also over. That's it. Thank you all.
Well, our All right, we're ready for the next presenter. So, yeah. So next presentation will be modernization for LogDep, and Bokenfang will present it from Microsoft. So please go ahead.
Thank you. Okay. Hello, everyone. My name is Feng Boqun. Today I'm going to present some idea I've been working on to improve LogDep. So for those who may not know that LogDep is an internal deadlock detector, so that it basically used to detect all the deadlock or the other log issue in kernel. And that's actually something that teach how a kernel developer will use how to use the log. Okay, so let's begin. Okay, so let's begin with some pain points of LogDep. So first one is everybody knows that LogDep has the warning of LogDep is not really human readable, although that it does provide all the information that need for a person to figure out that what's going on there, and for the people to really know how the deadlock happens, but it's really not do a better job as printing. And also, see this is example of there is 5 logs involved in this log issue, and the one I didn't show is that it will also print every stack trace of each log, but notice that LogDep can only record 1 stack trace for each dependency. This is because we do the thing in kernel, and we don't have endless. We don't have a lot of memory to record all the call trace of each log. So it's kind of a limitation, and it's kind of limited. And if you have ever been working on analyzing size one of the LogDep warnings, you will know that it's really once the numbers of log grows, and it will really take people a lot of time to kind of decoding that, what does that mean. And yeah, that's another part of this. Another pinpoint of the LogDep warning is that this is example. It's the same one as previous slide. So in this print, it seems that we only have 3 logs involved, and also in the possible logging scenario, it seems that we only to reproduce the deadlock, we only need 2 CPU. But this is not true. We print that because we do the pre-printing in C and in kernel. And first, we don't have a pre-print library in kernel, and I will assume that we will never have it in kernel. And the other thing is that we also need to have a way to maintain the space of the console logs. So you cannot do, so for this example, it actually may get like 5 CPU involved to reproduce this deadlock, but we cannot do the printing to exactly we cannot do the printing of the exact logging scenarios because of this limitation. So this all caused because we do the pre-printing in kernel.
No. Hey, can you hear me? Okay. Being the author of the code that prints this out,
yeah,
I took a shortcut to do it this way just because the screens at the time, I'm like, okay, let's just make it a little bit nicer.
Yeah.
It can and it should be updated. I just never had time to do it.
Yeah.
So don't say that this is a hindrance. It was a shortcut. It can be fixed. It can show you the full lock chain nicely. Just takes time to do it. So don't say that this is like a hindrance or anything. It was just me being lazy and
Yeah,
if I get time, I'll fix it.
Yeah, I get that. I certainly understand that. I'm not saying that. I'm not saying this is actually something wrong, but I think that one thing I should point out is I kind of thought that the point of we actually print the full information in the kernel, because it will take a lot of time compared to this shortcut one, and it we also maybe so I don't think we have infinite wide of the console log maybe, and somehow we're going to hit the limitation of the print k if we're doing that. But I'm just saying that this is the current state of lockdap, and maybe we can do that if the whole thing is done in user space. Okay, so another pain point of using lockdap is that sometimes people is working on XYZ, but the lockdap keep running on ABC, and there is one behavior of lockdap is that whenever lockdap find a issue, it will turn it off, and so it will no longer detect any deadlocks, and it will no longer keep bookkeeping, and it will no longer bookkeeping that which task has holding which log. So I think that this is actually okay for lockdap design, because if you have a lock issue appear and the system may be already in the wrong place, and you won't want to continue to see if there is any other issue, because it won't get, in theory, won't get a more accurate result. But it would be better that if we can somehow provide a way to user that, for example, like they only care about logs in networking and they don't want to block by some log issue in file system and vice versa. So maybe good we can improve that. And there is other, in theory, the pinpoint of lockdap is that first, lockdap itself has a log, and it uses it to protect the log dependency graph. And so that somehow creates a synchronization point because that there may be issues that you can reproduce in production, but you cannot reproduce with lockdap on. And so it's better if we can kind of minimize the impact of the synchronization point. Also, debugging lockdap itself is kind of challenging because it's involved like graph searching and also all the printing there. And honestly, I don't think that it's kind of I think it's okay to do that in kernel, but it should be done something. If it will be very easy if we do that in user space, we get a lot of tools to use, so that would be better. And also, if you want to change the behavior of lockdap, and you can use, if you can have that in user space, it will be very easy to change. Okay, so a little bit of introduction of what lockdap does today. So it's basically a big thing. It has the per task log stack, which track every task for the log it's already holding or it's going to hold. And if the log is holding in interrupt context, it will use the interrupted task stack to track that log holding. And whenever there is a dependency means that a log is grabbed after another log. So whenever there is a dependency, it will go to add a dependency, try to add a dependency to a dependency graph. And the dependency graph the dependency graph has all the dependency that already happened in the system, and it will use the deadlock detector
to go through the graph to find whether a certain circle exists or not. And also, speak of which, I think also we also don't have for LockDAP is that we actually don't have very clear rules of each deadlock. So I tried to add some deadlock detection in the LockDAP, and I tried my best to add comments, but it's really hard to describe like the ground rules of all the deadlocks. So it's kind of this thing is still missing somehow in the LockDAP implementation. Okay, so okay, let's go to next slide. So what I'm going to do, I have actually have some experiment with this. I want to change the LockDAP structure into this thing. It will have a front end, a back end, also a middle layer is, I call it pipeline, but I'm always bad at naming, so I may be wrong. So it's still that the front end pass dependency into the back end, and the back end can implement it. It still do the same work, but it gives some flexibilities, and we will see later. So, okay, so how do I think it's fine. So first, the LockDAP front end will bookkeeping. As today, it will bookkeeping all the log holding information, and it will work even LockDAP is off. This is a behavior change because we don't do that, but we can. Doing this is quite simple. We can just keep a per task array, so that's easy, and it's actually no log involved here. You don't need to log because you don't access the dependency graph. And so it's doing so, it will give you the answer that which logs the current thread or which log a thread is holding. So that's kind of useful because that we have a lot of LockDAP assert in the code, and we have a lot of the LockDAP assert in our kernel code, and if we have the front end, we can simply use it alone without the deadlock checking, but we still be able to find a lot of bugs that miss the some bug that caused by not holding a log. And also, it will run very fast compared to the full version of LockDAP because you don't need to hold a global log for the dependency graph. And the backend, it still maintain the dependency graph, and it's have the deadlock detector, and it also can do pretty print, maybe. So the whole thing is that the backend can be run in user space because we will see that the reason later. We will see the reason later. So it's basically the same function as we have for LockDAP today. So it will be not much change to it, and it's just the same as today's LockDAP. It will be just a cleanup and a refactor. Okay. So also it can be able to implement it in user space and maybe in another language. I have tried this in Rust, so I have a working Rust LockDAP backend that. Okay.
Sorry. We have a question from Peter Z online.
Yeah, so if we do the whole log detection thing in user space, how does the message get out if your machine deadlocks?
Sorry, I missed your last sentence. Could you repeat again?
Suppose you have an actual deadlock and you do the log detection in user space.
Yes.
I think you're screwed.
Yes, but most of the time, LockDAP only detect the possibility of deadlock. So
if you're lucky.
Let me just so people do understand what's going on. If if LockDAP actually detects, or if there's a real LockDAP or deadlock, the deadlock could trigger before the backend gets to tell you it. So one of the features of, I've had several cases where the system locked up, but luckily LockDAP triggered, showed you the print, and then boom, you have the lockup.
Yeah.
So if it's in the user, I think Peter's concern is if it's in user space and that happens, you get the machine just locks up, but you have no report of it.
Yeah, so I understand that. What I'm trying to say is that with this front end back end design, you still have the old behavior of LockDAP. You still will have, you still can have the the back end running in kernel. It won't change the old behavior. It just provide a flexibility to run the back end in user space and have a delicate front end so that it can track all the log holding information.
So maybe I could rephrase what you're doing. So basically, if you're worried about locks, things locking up, and locked up is, so basically the idea of this is if it's in user space, you could implement different functionalities so that in the case you have is you're testing your code, but there's some other code that's triggering locked up splat for some various reasons. And sometimes it's something that's like, RCU stuff is important, but there's very, very seldom does it actually trigger a true deadlock because it's such, the reason why we have locked up on it is because it's such a hard race to hit. It's likely it's not going to be your problem, but there's cases like when I'm working on the RC1, RC2 kernel, that there's a locked up splat, and I'm like, oh darn it, I can't use locked up to debug my own code that I'm developing on right now because this splat always triggers first, and I never get to test my code. So if it's in user space, even though the splat happens, it's not going to disable locked up, and I can still continue to test my own code.
Right.
Is that what you're proposing?
Yes.
So Peter, does that make sense?
I'm worried. I mean, the primary usage for LockDAP is during kernel development, and we want people to use this all the time. If you're moving a whole bunch of that functionality out to user space, people will not quite know which to use, especially if the user space one grows more features. And that just fragments things. Like Steve said, I've hit that actual deadlock case quite a lot during my own development. That really is a valuable thing to get LockDAP output before the machine locks up. So I'd really like to keep the whole thing in kernel space. Splitting it up as you do, that's fine. Right? I mean, writing the whole thing in a different language, perhaps. I mean, we'll possibly get that whole Rust thing in the kernel.
Okay.
There's that. So yeah, refactoring how the whole dependency tracking thing is done, I don't mind too much, but keeping it all in kernel, I think, is really important.
Yeah.
So Peter, I just want to understand what you're saying. So you don't mind the rewrite, or you don't mind the restructuring, you don't mind all this, as long as it stays in the kernel and the fact that it will trigger before the actual lock happens, or lockup happens.
Correct. If it also exports data to user space and we get a pretty printer that prints prettier or more comprehensible output, I'm fine with that too. But adding features that rely on user space for critical things, that's just not okay.
Okay. So let me see if I understand that correctly. So basically, you want if we have this functionality in user space, you want the user space and the kernel share the same deadlock detector, right? I mean,
Correct. The basic core code should be the same. The kernel could have a simpler printer, just dump the bare information.
Yeah.
And user space could grow a real fancy one that holds the hand. But I really think it's important to get all the information out if you had an actual deadlock.
Okay.
Just wondering whether you could specify a kind of machine interface to dump the data or the intermediate data for consumption, either by user space, by some after a kexec, some other kernel that could run after the deadlock, or from within the kernel. Yeah, I mean, that's a common thing to do.
Okay. Oh, by the way, while I was working on this, I actually decided that I should keep the deadlock detector the same in the user space and in the kernel. So it won't be like more functionality of the deadlock detector in the user space than the kernel. That's the thing I try to keep the same. So okay, maybe we can go on. I have a few slides about something. Okay, so the middle layer, the middle layer can be, it's just transfer the dependency information from front end to the back end. It's actually abstraction, but know that it may be, so it can have an optional dependency graph also in the middle layer because we want to save the dependency. So if we don't have the cache of dependency graph, then every dependency will be treated as a new dependency, and sometimes it won't be necessary because the dependency has already been seen by log type. So it may have actual another dependency graph, but this only exists if the backend is running in user space or in other machine, and it can have multiple mode for the pipeline. So if we define the pipeline as just function call, then it just behave like today. It won't have any other. It probably have better code organized, but the behavior will be the same as today. And I think that we actually want this because we want to have today's log type in at certain level of, as you already said, at certain level of the development cycle, because that means that we have the zero deadlock tolerant policy. So that is an important thing. And another thing I have experienced is that I can use it to I basically just use a proc file to get the information to the user space, so the user space can run the detector. So it's running, and it's actually can do the dependency check. And also another thing I'm trying is that I actually run the log depth backend in another machine or in a host that the information is dumped via the serial console. So these two are the use cases I think may be useful, especially for some CI people, because it maybe give them more flexibility to run their tests, and it could potentially detect more log issues ahead of time. Okay, so yeah, that's basically I'm about to talk today. And the future work is to upstream. And I think the front end isolation is actually straightforward, and it can be done very quickly. And but I have been stuck at the configuration, so I need to make the configuration works that we have multiple mode of the pipeline layer, and we have multiple. We are able to have multiple backend. So that's something I'm working on. And also the thing I haven't mentioned is that I'm not sure that if we are going to allow this to be in a user space or another machine, that what will be the protocol of the pipeline. So basically, it's like a tracing. It just send to another end information. So, but I'm now using a very stupid way. I just put this structure into the memory and print it out. But I think maybe that's something I can work on. I can seek some to see if any tracing format can really fit this usage, and also whether we will have multiple backend in the kernel. Okay, that's all. Thank you.
I have a question. The log file itself is pretty big. I think maybe around several thousand line, maybe 7,000, 6,000 or 7,000.
Right.
So have you thinking about breaking up into smaller portion corresponding to different part of the like the front end and back end?
Yeah.
So make the file smaller so that you can people when they look for information, it's easier to look up than just one big giant file.
You mean like? Let me see if I. You mean moving the? You mean like code cleanup?
Yeah, just depending on the function, you can put it into different file so that.
Right. Yeah. That's yeah.
Easier to find the information instead of in a big file.
Right. That's something I will do for with this effort. In this effort, that's something.
Yeah, because I actually have been thinking about whether we should just break up the log file into a few smaller pieces to make it easier to understand.
Yeah. I think it's good thing to do even we don't choose the front end and back end, or even we don't allow to run it in user space.
I have this kind of problem. Sometimes it's hard to look for information, and also there's a lot of conditional comparison code. There are different conditional. Oh, sorry. And sometimes it's hard to figure out whether they are enabled or not, or whether you put the function in the wrong place.
Yeah.
Under some certain configuration, it won't compile.
Yeah. So I started this work because issue like use that, and also while I started it, while I'm working on it, I figured that maybe we can do something fancy like putting the backend in user space. So
yeah, I understand that, but while you are doing that, you should also think about how to simplify the log file.
Yeah. Any other question?
Looks like no questions.
I'm not very familiar about what's being done in this backend, but I mean, I'm thinking maybe there are other use cases rather than moving that to user space. I mean, it could be moved to after a kexec. It could be maybe moved to after some dump over a network interface. Things like that maybe could be done. So what additional things could be achieved if we can move optionally the analysis or this backend over there, rather than just in the kernel at the moment where things are locking up?
Really, let me think. I don't have any idea right now, but The illustration is actually valuable. I think maybe, right, if we can do that, as I said, after a K execute, that will be as kind of, that means less work for us to like refactoring the whole thing and still keep something because you got a brand new kernel to analyze that. So yeah, that's maybe, but then I think so one information I'm not really sure about is that I don't know how the CI people will run this, whether they will benefit, whether we do the KXQ thing will benefit them. So that thing I don't know. I mean, maybe they just like to take a lot of log and have their script to analyze them. Maybe that's what they want.
Yeah, I mean, it's one thing to look at the technology, how can we move things around to make it different? But I mean, it's important to ask ourselves, what are the additional use cases that it could enable? And it's not clear to me. I don't know what's the information content well enough and what the current backend does with it and what it cannot do because it's limited in its execution.
One thing if you do the KXA way is that you don't need to have a way to figure out a way to pass all the stack trace into the backend. That's a lot of effort for everything. Maybe so. I'm also worried if I run a backend in user space that the transaction of the information of the stack trace will take a lot of time to process and for the kernel. So it will take a lot of CPU times and still run, then make that locked-up run even slower without compared to the current situation.
Yeah, okay. So by kind of serializing the data that you need.
Right, yes.
I don't want protocol, for instance.
Yes.
But I mean, it might be worth it if there's more features or more things that can be done.
But as Peter said, that we cannot have. I think we don't want to have more feature in the if we change that in the user space, and because then people will use that. We will use that instead of keep the kernel version of that locked up complaint. So they will they may change to if what I'm trying to say is that if we're going to make the user space version of locked up more powerful, then it's probably not what we want because we want them to be as same as powerful as kernel version. That's what I'm saying.
Yeah, I mean, those features might not be available to kernel developers who typically use it from their console or things like that. Yeah.
Thank you.
Thank you.
Any other questions? No? Right.
Thank you.
Thank you very much.
Thank you, everyone.
And now we have a break. I think. Well, yeah. Until 5.
Hello. Hi, everyone. Thanks for coming to this talk. I'm Joel Fernandez. I work at Google. I work on Chrome OS, on scheduler, performance, power, RCU, stuff like that. Yeah, in this talk, we're going to discuss some RCU issues. So I would like to introduce my co-presenter.
Hello, everyone. My name is Latreski. I have been working in Sony Mobile. Actually, I'm doing kernel developments and I'm doing performance, power, thermal, sounds like that. Yeah.
Hi, my name is Rishikesh Kadam. I work for Intel. I have been previously working on firmware mostly, so SoC IP firmware, SoC power management, microcode, and then power and performance tuning. And most recently, I have been working on power and performance optimization for Chrome OS and Linux-based Intel devices.
Okay, so in this talk, we're going to discuss RCU at a high level, not in explicit details of how it works, but just at a little bit of high level so that we have enough background. We're going to discuss two of the main issues we found with RCU, mostly related to power and how we see that it can have tendencies to disturb an idle system. So basically, just to summarize, we see that in the default configuration, RCU can keep the scheduler tick turned on when the CPU is idle even, and there are callbacks queued. This can hurt like idleness. And we also see another observation with RCU that it can queue callbacks, very few callbacks very often that are not that critical to the system, so it can disturb like an idle system. So we'll discuss these issues and possible solutions, and I will try to get through the content and keep questions for the end if that's okay. Definitely, we'll try to address questions at the end or in the hallway. So with that, next slide. Okay, so at a high level, this is the most popular use case for RCU, which is data structure read modification concurrently, right? So in this use case, what happens is we have something called an RCU read lock, which is acquired by a reader before they read some data structure that is being protected. And then we have a writer that is attempting to modify the data structure. And this has to happen concurrently. That's the main selling point of RCU is you can do this concurrently. So the way that is done is the writer creates a copy of the object being modified, writes to the copy, and then switches some pointer that is pointing to the data structure to the new copy. However, it needs to wait for it has to garbage collect the whole copy, right? Otherwise, you'll run out of memory. So it has to do so after waiting for a certain amount of time to make sure there are no more readers that have any references or possibility of accessing the old object. And that's where the update phase comes in. So that's what read, copy, update is. That's just at a high level, the most popular use case. However, it's important to note that this is not the only use case for RCU. There are several different, very clever use cases of RCU. And they all need the same basic tools, which is they need to start and stop a critical section locklessly. And we can call that as we can call those critical sections as a reader for the purposes of this talk. They may not be doing any reads or anything, but let's just call them readers. And then we need the ability to start waiting at some point in time. Let's call that time T0. And we need to stop waiting at some point in time. Let's call that T1. And we would stop waiting only once we confirm that all readers that existed at time T0 are no longer running. Like any reader that was in the critical section that was marked by the markers are no longer running. That existed at T0. If they started after T0, we don't care about those, but we care about the ones that were there at T0. So one way to accomplish this would be, at T0, you queue a callback, and when you decide that time is up and it's time to stop, then you would execute the callback. So we can call that as invoking a callback. So this is what happens on a local CPU running in kernel mode when a callback is queued. That's the same T0 we were just referring to. So the CPU is in kernel mode and we queue a callback T0. Now we have the scheduler tick that is continuously running. And just to clarify, this is with the default RCU configuration. There are other RCU configurations that do other things, but with the default one, we see that the timer tick constantly has to run at the Hertz rate and has to check whether there are any readers on this CPU since T0, right? And if there are no more readers, it reports to this global thread that there are no more readers. But it also has to do something else. Because a callback has been queued on the local CPU, it has to also check if all other CPUs have also confirmed that there are no more readers, right? Only then can it execute the callback. So it executes the callback on the same CPU that queued it after it has confirmed that it has, there are no more readers on the whole system. That was kernel mode. So now when you look into CPU idle, right, your idle, and say just before you went idle, a callback was queued, and then you went idle. Now the timer tick still has to fire, because according to the previous slide, we have to confirm that all CPUs have reported that there are no more readers. However, we don't need the upper arrows, because there cannot possibly be a reader on the current CPU active, because the CPU went idle. So there's no way that is possible. But we still have the other activity, which is we need to check if all the other CPUs have reported that there are no more readers, so that we can execute the callback that was queued, right? So you can imagine the CPU is idle, and we have these ticks that are constantly firing to check if RCU has terminated, and we can execute the callbacks. So this can, severely hurt power. It's interesting. We had platforms where we didn't even know this was happening, and that is the reality of it. So we can show you some traces. So if you want
Hi. So this is something I discovered very earlier this year. So we were running video playback on an Intel Alder Lake-based CPU and on a Chromebook. And we saw that there were like a 2500 wakes per second that were happening during a video playback use case. And more than that, we were seeing that we had a very poor package C state precedency, which is the low power state for the SoC. And but the CPU utilization was very low. So we wanted to figure out what's going on. So on the right-hand side, you see a snapshot from kernel shock during the local video playback use case. And what you see here is, so the vertical blue boxes here are the video frame boundaries. So this is where the audio video is decoded and rendered within those blue boxes. And then the intervals between the blue boxes is the idle period where the CPU should go into a low power mode. But what we observed is a problem. So if you see the horizontal red boxes, those are some instances we observed where the CPU idle tick was staying on, and it was staying on because RCU was keeping it on. And that was having some impact on the power. Now, so in the next slide, I don't want to talk about why the tick being idle is bad, but what I want to talk about is how bad it is, because I think everyone understands that having the tick is a bad thing, but I think until this point, at least I did not know how bad it could be. So in this particular use case, if you see at the top, we have this graph, and on the top graph, what it is doing is it's showing the CPU C0 state, so the active state per CPU. So you have the left-hand side on the top graph and the right-hand side. And the left-hand side is where you have the default case at that time, which is you had these occasional ticks that I showed in the red box. And then on the right-hand side is the case where once we fix those ticks, this is the CPU residency or load. So between the left-hand side and the right-hand side on the top graph, there is actually hardly any difference in terms of CPU C states. They are almost equal. In fact, the only difference, the difference between the combined CPU load on the left-hand side versus right-hand side is less than 2%. So the ticks actually do not put any load. But that is where I want to show the bottom graph. So the bottom graph is the package C state for the same configuration. So again, the left-hand side is with the occasional ticks, and the right-hand side is once we fix the problem. And what I show in the bottom graph is the package C state. So briefly here, so I want to describe what the package states are. So the PC0 is the active package state. That is the one shown in blue. And then the other ones are deeper and deeper levels of low power states. And the green one is the PC8, which is the lowest or the deepest package state you can have for this use case. And as you can see, between the left-hand side and the right-hand side, with and without tick, there was, once we were able to resolve the ticks, we were able to see like a 25% jump in the deepest package C state. So from 18%, it went to 45%. And it improved the SoC power and the memory power combined by 10% for this use case. And so the one key message I want to mention is that if you're trying to optimize your multimedia stack using the regular tools like FlameGraph or ftrace, this 2% load from these wakes is negligible and you'll miss it. So you probably want to look at the package C states as well if you're on Intel platform, but also maybe applicable for other SoCs. And you want to look at the wakes because that is where some of your power problems may lie. And so Joel wanted to emphasize how bad the ticks are. They're eating up into your battery. And so now that I talked about package C state being impacted so much, I want to talk briefly what the package C state are and why do we see this kind of a behavior. So before we talk about package C state, let me quickly touch upon what C states are. I think most of you may know. So traditionally, ACPS C states are CPU low power states. So the CPUs will typically report their exit latency and then the power break even time. And then you have an you have an idle governor that picks the C state based on the OS next event prediction, as well as the particular C state's exit latency and target residency. And typically the CPU C states, the per CPU C states have a very low exit latency and target residency of the order of tens of microseconds to maybe 100 microseconds. So the ticks themselves do not significantly block. You can still enter the deepest CPU C state. Now, what is the scenario with a package C state? So what is a package C state? So last 5 years ago or so, we started having system on chip architectures for laptop. And what the system on chip architectures do is they have like a power management unit which can then coordinate, or which can look at the state of various CPUs as well as various the IP blocks in the SoC, as well as common logic like Fabric. And then it can use hints from the OS for the idle state, and along with the rest of the information that is available within the SoC, it can put the entire SoC in a low power state. So that is what essentially the package C state are in this architecture. So basically and the way we use them is on the right hand side, this is a table for the Alder Lake C states latencies and residencies from Intel idle driver in the tree. So the last two entries here, C8, C10, you can say are the package C states. So these are the states where the power management unit is actually using these OS hints for the C8 and C10 to put the entire SoC in the low power state. Of course, looking at the rest of the SoC components as well. Yeah, sure, please.
Yeah, so the main takeaway is that it's extremely expensive these days to disturb a CPU in the idle state, right? Because the whole SoC goes into this low power state, and it's much more expensive to come out of it.
Right. And the thing I want to emphasize is it's not like package C state is the culprit, right? I mean, with this additional logic, you are able to enter deeper C state, so you have lower power today than previous generation. But if you want to take advantage of that, then you really have to look at your wakes of the order of ticks. Previously, what would happen is you would look at wakes which are within tens or hundreds of microseconds, and you may neglect the wakes which are in milliseconds because they are too far off and they do not impact power. But if you want to use this extended deeper C state, then you also want to care about the package C state. So here, For C8, the target residency is like 800 microseconds. So if your tick is 1 millisecond, which is the case for the Chromebooks, and we have multiple processors running the tick, then you are probably going to block the package C8. So you want to look out for those high latencies. And so I talked about the problem and the impact, and now Joel will explain how we will address it.
Yeah, so if like, if in certain configs, keeping the tick on during idle is so bad, then why does RCU do it, right? And this is again to support the use case where there is a desire to execute callbacks, RCU callbacks on the same CPU they were queued. And the advantages of doing this are, all the advantages you can think of for the per CPU execution of something, right? Like keeping things on the same CPU. So cache lines are hot when you queue a callback. So executing the callback will access some of the same data structures. So you'll get the cache benefit. Also executing callbacks on the same CPU. All these callbacks are in a list. So executing on same CPU means you don't need to do locking. Whereas if it was on some other CPU, you need to now synchronize the queuing and dequeuing of callbacks. And then the other benefit is elimination of locking and lock contention. I mentioned that. Thread wake-ups, yeah. So yeah, if you were to like execute callbacks on another CPU, you would have to probably do it in a thread on another CPU and then acquire some kind of lock to synchronize, stuff like that. So
I can also mention one thing, that it's when we're doing this per CPU, it means that we are really good to number of CPUs. So it's actually scale it to a number of CPUs, and it's good for big systems.
So for busy systems and large CPU systems that don't necessarily maybe care about idle power or something too much, maybe it's okay, but it's not okay for us. Say we don't want any of these advantages, and we just want the tick to be turned off already, when the CPU is idle. For this, we have a config RCU no CBCPU. And this is something those who care a lot about embedded systems, power, so forth, should really look into whether they have it enabled or not, because apparently not everybody knows about it. And the idea is that, again, like, you have a thread that executes callbacks, so they don't need to anymore be queued and dequeued on the same CPU. So when the callback is queued and CPU goes idle and the tick is turned off, now that CPU doesn't need to have the tick on anymore when CPU is idle. Obviously this now has the disadvantages which were previously advantages, right? Now you have locking and these kind of things. So it depends on your use case. If you have a lot of callbacks being queued and stuff like that, maybe it's not a good idea. So you have to test and see what happens. There could be performance regressions. But for power and isolation of CPUs and things like that, it could be a very good idea to do. And config RCU no CBCPU moves both the grace period start and the execution of the callbacks to the thread. And another thing to note here is that because the callbacks are executing in a thread, it is possible for energy-aware scheduling to move the threads to low-power CPUs and keep the big CPUs idle and with the tick turned off, right? So it's great for power. The experiments show that there is almost a 25% difference in power with using config RC no CVCPU. It's funny that when this was config RC no CVCPU was developed, the use case wasn't power at all. It was something else. I believe CPU isolation and HPC, stuff like that. Frederick can comment more on that, but it does save a lot of power, as we see. And to make it easier for people, so just enabling config RC no CVCPU is not enough. You have to pass a boot parameter that tells RC which CPUs need to, queue callbacks and execute them in a thread and things like that. So to make this easy, we added a no CVCPU all boot option. So if you enable, sorry, not boot option, config option, And if you enable that, then you don't need the boot parameter anymore. So the next question is, can we do even better? And this is the observation we see, that on a mostly idle system, we have these few callbacks that are queued constantly, even when the system is relatively idle. We call this a trickle kind of effect, where you have these 5, 10 callbacks that are constantly being queued. And every time this happens, it's very disruptive. So I wrote a tool called RCU Top, which I will hope to merge into the kernel sources, where you can monitor at a high level all the RCU callbacks that are being queued and executed in a periodically refreshing interface. And we see, on Chrome OS, at least, we see that several callbacks are constantly being queued when the system is just doing nothing. And every time that happens, it's very disruptive. This is a trace of just the device doing nothing and the display is on. And every 16 milliseconds, we see in yellow that the closed system call is queuing a callback and triggering the entire RCU machinery. This is because the display pipeline opens and closes graphics buffers, which I believe is DMA buff, and that triggers, just opening and closing those buffers triggers RCU. So with this, Vlad will share his experience on Android.
Yeah, hello again. So I would like to talk about Android workloads, and what I need to mention here is that if you want to save battery life and battery, please use config RCU no CB, because as Joel mentioned before, so everything happened in K-threads, and all these K-threads can be run on any CPU, and it's up to scheduler to decide where to put a task to invoke these callbacks. And when it comes to energy-aware scheduling, so it's a good choice for it to decide where to invoke such callbacks. Yeah, so here I would like to talk about a little bit about static image use case. That is, here I would like to talk about static image use case. That is probably the most important in Android workloads. So basically, all of you daily run into such use case. So it means that in these states, we would like to save power as much as we can. So it basically means that CPU stops refreshing panel, and it switched itself to itself refresh rate. Then CPU spend most of the time in deeper C states. SOC bandwidth is minimal, memory bus, L3 cache, and everything run on its minimal capacity, because the idea is to save power. So, and what we observe in this static use case, that we have kind of login system, and it does a lot of opening and closing file operations. And these actually operations, they apply pressure on RCU subsystem. And as a result, in this test case, static image use case, we have a lot of wake-ups coming from RCU subsystems. So on the next slide, I will show you. Okay. Yeah, this is actually trace output, ftrace output, but it's a post-processed ftrace output, and it's actually no CB CPU configuration. And you can see that in static image use case, so the trace was taken during 30 seconds. And in this test case, you see that most of the wake-ups that we run into belong to RCU OP and RCU OGK threads. So it's a 40,000 each. And yeah, a trace was taken on ARM big little system. So, and according to this trace, it's obvious that RCU is the main resource, a source of wake-ups. On this slide, you can see that most of the wake-ups actually so it belongs to VFS file system and SE Linux subsystem. So during the login, and these two subsystems apply pressure on RCU doing memory reclaim. And you can see it's a file-free RCU operation, inode-free by RCU, iCallback, D-free, and AVC node-free. And the most point with this is that we only invoke 1 to 10 callbacks only during static imaging use case. If you go next. Yeah, and on this slide, you can see that I traced RCU batch start RCU events. And you can see that mostly 4 CPUs, it's a little cluster, a small capacity cluster. It's disturbed by these wake-ups, and the time between all these wake-ups, 6 to 7 milliseconds interval. So what is quite a lot. Then I bypass to Joel.
Yeah, so let's explore some possible solutions to this and drawbacks and so forth and where we are today. So one of the things that can be done is to set the Jiffy still first FQS boot parameter. And what this boot parameter does is it delays any RCU processing at all when a callback is queued by those many Jiffies. So this sort of can be used to see what the light at the end of the tunnel looks like if you don't execute RCU callbacks for a long period of time. Well, not callbacks, but if you don't do RCU grace period processing for a long period of time and then you finally do it, so this sort of just using this, we can see that there's 3 to 4% power we can save on top of RCU no CB, which is significant. And there are some problems related to doing this. As I said, it's not something you can do, which we discovered that it's not a production option. And I will discuss the issues. So right off the bat, we see that running the Chrome OS tab switching test, where we switch between 2 tabs in the Chrome browser, we see that latencies go up because something in the kernel does synchronize RCU, which because of the Jiffy's till first FQS change that we made, the latency of that goes up. We see that ftrace, so running ftrace itself slows down, at least when you run it with trace CMD, because it does like various things like writing to the set ftrace PID and things like that, resizing the ring buffer, which also calls synchronized RCU. So I saw that trace command record function graph can take like minutes to finish running and stuff like that. Another case we see, this we saw with Chrome OS boot up, is that I found out the hard way that synchronized RCU is actually on the critical path of our boot up, of our, once init loads and everything, because we enforce SE Linux, and SE Linux also does synchronize RCU when it does the, enforce stage. Another use case which does use RCU is the per CPU reference count primitive in the kernel, which has 2 modes. One mode is it modifies the ref count in a per CPU basis, and then it switches to this atomic mode where it does this atomic per CPU, atomic ref count increase. And switching from the per CPU ref count mode to the atomic mode requires call RCU. So we would slow that down as well with the Jiffy still first FQS. So this this example shows us that we cannot assume in the kernel that all RCU users reclaim memory. We know most of them reclaim memory or something like that, but as I was showing you earlier in the slides, that's not a valid assumption, and this certainly shows us. So we cannot use Jiffy still first FQS. However, we also tried using the expedited boot option, which speeds up synchronized RCU. However, it still does not return our boot performance regressions with using Jiffy still first FQS. And this slide shows us that the boot time, the power, we see power improvements with no CB. And then with Jiffys, we see the 4% power improvement. However, the boot time goes up significantly. And then we can get some of that boot time back by using the expedited RCU boot option. However, we don't get all of it back. So Jiffys is just not at all a possibility. So what we thought was, looking at this problem, 10 minutes? Looking at this problem, what is needed is selectively, if we can identify RCU callbacks that can be, identified as just delay these ones and don't delay everything on the system, then maybe we can get somewhere. So we started thinking about a new API called Call RCU Lazy, and it's an V5 right now, patch series, and there are several things we have to be careful about: RCU barrier, hot plug, memory pressure, where we cannot indefinitely delay callbacks that have to reclaim memory and stuff like that. So this slide just shows how complex grace period processing is. When you queue a callback, all of these stages happen, and it's really, really intense. And the idea is to just delay all of that if only callbacks that are annotated as lazy are queued. So we wouldn't do any of this heavyweight stuff when only call RCU lazy callbacks are queued. And so we came up with several design approaches. How are we doing on time? Okay. Yeah, I think it's good. So we came up with different design approaches. One of the approaches the latest approach we tried is to use this thing called the bypass list. So so there's this thing called the bypass list. Let me explain that briefly, what that means. You remember I told you with no CB CPU, we have this lock contention that is now introduced because you have to lock the callback list. So that actually has been compensated by this thing called the bypass list, where if lots of callbacks are queued, we queue them into the bypass list and only flush them out to the main callback list after 2 jiffies. So we have adopted this approach where we reuse this bypass list. And we basically put it into overdrive. So instead of 2 jiffies, now we want something like 10 seconds. Like, just keep them in the bypass list. Don't let RCU know about them. And we have protections. Like if there's memory pressure, then we flush the bypass list. Or if the 10 seconds or whatever number of seconds have passed, we flush the bypass list. So with this, we can actually hide the callbacks temporarily without letting RCU know about them at all. And we see that this gives us the same kind of power improvements we see with RCU with the Jiffy still first FKS boot option. In fact, is it more? Or I think it's about the same, 4% or so. And we get the extended C state residencies that Rushikesh was talking about. So it's pretty good. And this is a link to the patches. You're welcome to check them out. I hope the V6 should be out in 1 week or so, and then it looks promising. Paul is very supportive with merging it and so forth. So with this, Vlad will talk about his experiments of Android with these patches.
Yeah, briefly. Actually, it's another test case. It's a home screen swipe, and on the top you can see that it's the same. It's RCU batch start traces, and you can see that we have plenty of them. And such behavior or such pattern, it's actually makes a lot of noise for when it comes to wake ups. And thanks to scheduler that it makes use of only 4 CPUs. If we, for example, if we used a high capacity CPU, power drain would be much more worse. So after applying RCU lazy V6 variant, you see that we actually eliminate noise completely. We have only few events. And if you go down. Yeah, and also I just, as an example, I took a power, I put some power plots of this home screen swipe test case. So actually on the top you see default variant, and on the bottom you see patched variant. So we have approximately 3% delta, but we can detect it. It's constant. And also, I need to mention that it also depends on the platform, because in our case, it's ARM platform. It's pretty good optimized when it comes to idling CPU, waking up CPU, and so on, comparing to Intel platform. So it depends on platform. So, but as I mentioned before, 3%, but it's we can detect it, and it's repeatable.
With the panel turned off, it's probably 6%.
Right? Yeah.
So running the same tool that I showed you earlier, the output of like RCU top, we see that the callbacks are only getting queued and not executed. So this tool is sort of like really handy to confirm that, confirm which callbacks are getting queued constantly and which ones can be made lazy. Obviously, converting call RCU to call RCU lazy is something that a subsystem maintainer has to accept as a patch. So once you identify a callback that you feel like is unnecessarily having the sense of urgency, you can send a patch to fix that. And we'll certainly send patches as well. And there are some drawbacks of using this, which I want to be clear about. So one drawback is if, like, say, some subsystem writes a new driver or something like that that queues a new RCU callback but doesn't use lazy, then that would again like bring us back to a situation where RCU activity can cause noise and disturb the CPU idle and so forth. Also, there's a risk of call RCU lazy accidentally being used, like if the user doesn't know what they're doing and they use call RCU lazy when they really want the callback to be executed soon. That can probably hurt their use case. And this comes back to documentation. So we are going to be doing our best to document the new API and make sure everybody understands how to use it. And there is a risk of memory pressure, right? Because we're really severely delaying RCU callbacks. We do have a shrinker, and we have taken our precautions about this. But we're not entirely sure if there's some extreme condition where memory pressure will the system or something. We haven't seen it, but you never know. So testing is in progress and so forth. So with that, we're done. I really want to thank some people like Paul McKinney for mostly putting up with us and helping us out and all this kind of stuff, and to Vlad and Rishikesh for really like supporting me and moving this work forward. Without them, it's not possible. And all our sponsors and organizers for this conference, because it has been really useful, especially for this work. And also to Frederick Weisbeck for really like reviewing the code and finding out lots of issues, with the code and so forth. So with that, we have 2 minutes for questions, and then we can talk in the hallway as well.
All right. So this is very useful information. I had firsthand experience with call RCU regression in Android. So it took me some time and actually Paul's help to figure out what it is. It would be really nice to document all the kind of downsides of enabling no-CD configuration.
Yeah.
And it's not apparent that actually call RCU might not just the scheduling of call RCU might not only be delayed, but the call RCU itself might regress because of the additional logging. So if you have a lot of call RCUs, they will regress your fast pass, which, calling call RCU, you don't expect it to take longer with this new configuration.
Yeah.
So it would be really nice to have a list of possible downsides.
Okay, yeah, let's talk about that. And I'm interested in your use case where you see the exit path. I remember you telling that it regresses, so this might help that.
Yeah.
So let's go to the next question.
And one more quick question. Will there be any API to drain the lazy as a bypass queue?
ABI?
Yeah, well, so in my case, I had to.
Yeah, no, there's no ABI change. Literally change it to _lazy, and that's it. We handle everything behind the scenes.
Okay, so in my case, I had to implement pretty much the same idea, but I also need drain API to basically, when process exits, it needs to say, okay, I
think
actually
let's
need
talk
to
about
destroy
that.
that.
Yeah, I think we can take care of it. Yeah.
Okay, cool.
Hallway. Last question. No.
I'm sorry, we have a hard cutoff at until the next presentation.
There you go. Previous. Is it keyboard better or? Yeah, I think so. You can also like do the keyboard part again. Good luck.
Good afternoon, everyone. Keeping the topics light, after a talk on read copy update, I'm going to discuss restartable sequences. My name is Mathieu Desnoyers. I am a CEO at Efficios. I do mainly kernel and user space tracing with LTTNG. but I also I'm maintainer of the co-maintainer of the restartable sequence system call and membarrier system call in the Linux kernel. So whatever I do, I mainly do for the sake of speeding up my user space tracer, but I keep in mind other use cases, such as memory allocators, which is the one I'm going to target mostly today. So this presentation is about an improvement or an extension to restartable sequence, which is to add a scheduler-aware scaling of memory use on many core systems. Yeah, so Okay, a quick outline of this presentation. So I'm going to quickly brief you about the RSEC use and adoption status at the moment, discuss the next steps, introduce the per memory space virtual CPU ID RSEC extension, discuss the impact on scheduler context switching, present benchmarks, stat profiling, discuss NUMA aspects, and then open the discussion. By the way, please ask questions during the talk. No problem there, and I think it's good to clarify things as we go. So the current status, the architecture supporting the sysrsec system call ARM. So all of those architectures that have 3264-bit, it's supported on both. So ARM, MIPS, Power, RISC-V, S390, and x86. CSky and Long Arc have RSEC system, the RSEC system call implemented. However, they never provided any code for the self-tests, which I don't really like. So I asked the CSky maintainer to provide that. So he should be doing that soon. Long Arc, it's unclear whether they will be providing that. So personally, as a maintainer, I prefer to have RSEC not available in an architecture so that user space can have a fallback that works well and know that when RSEC is there, it's good. So yeah. In the GNU-C library in version 2.35, RSEC has been, the RSEC support has been added, and it's being used to implement sched-get CPU. And they get nice speed ups, especially on architectures like ARM64, where sched-get CPU is not implemented as a VDSO. So you go from a full system call to a load in user space. So it's a nice improvement. There are other use cases being discussed, mainly memory allocators. So there's tcmalloc, a project from Google, which uses RSEC now, the RSEC system call. They've been using their own internal RSEC before. CRI-EU supports RSEC now, Dynamo Rio as well. So, yes?
So get CPU, I guess so it's a memory load. What can concurrently modify the CPU number? Like, isn't it always fixed, or is it hot plug?
It's the kernel. So the kernel, as it migrates the thread, is after migration. So migration raises a flag, then you get to resume to user space. At that point, you can take page faults. So at that point, the kernel updates the content of this per thread area.
Okay, so now you can directly read it from user space.
Yeah, so whenever user space then loads the value, then it's the updated value.
Okay, got it. Thanks.
Welcome. So next steps, targeting use cases, memory allocators, ring buffers, tracing everyone, yes. Counters, so we have new features coming in LTTNG, which is based on counters, and I plan to make use of RSEC pretty soon for that. That's going to be nice, nice performance improvements. And generally, RSEC can be used to remove the need. Okay, so next step, just a bit of context. So when designing things like memory allocators, you basically currently have to choose between a global, you're in user space, you're in a process. You want to choose between, let's say, a global arena with locking. If you have very few threads, that might be a nice trade-off. Uses fewer memory. Or you go for per thread, But then with per thread pools, you have nice locality when you allocate. But then as your threads, number of thread is going beyond the number of cores, then you start to waste memory compared to having a per core approach where you would like to have ideally per core memory arenas to allocate from free lists, right? So what I'm going to present today removes the entire need to choose between those three. More on that coming. Some use case, so when you use RSEC, RSEC is good for doing per CPU data accesses. But the thing is, per CPU data in user space, if you are in, let's say, in a single threaded application, you're wasting memory. I mean, you allocate per core data structures, but then you have only one thread, which might be freely being migrated between all those cores if it's not defined. And yeah, you're bad at locality and you're wasting memory. The other use case is per CPU data memory used when using CPU sets on many core systems. So let's say you have a big system, let's say, I don't know, 256 cores, but then it's fragmented into small CPU sets, small containers. Each container has a full view of all the 256 cores on the system. So if you go for a per CPU data allocation, you'll allocate 256 entries, right? So again, that's pretty bad. Because I mean that you could be using CPU sets to limit each container to maybe 4 cores. So here comes the per memory space virtual CPU ID restartable sequence extension. So I did not came up with this idea. Paul Turner was discussing it with me at Plumbers 2019, and this was actually my last Plumbers, so first travel in 3 years. So the idea there is to allocate virtual CPU IDs within a process which can be limited by the number of threads which are running concurrently. Okay, so let's say you are a process and there's only 2 threads and you want to index per CPU data. Well, you'd be good enough with index 0 and 1 because you only have 2 threads at most running, right? And whether it's because there's only 2 threads in the process or because that process is always assigned to only 2 cores, I mean, globally in the system, you only have 2 entities running concurrently. So you just need really 2 entries in terms of per CPU data structures. You just need to make sure that whenever 2 threads from that process run concurrently, they never think that they have the same ID. They each need to have their own temporarily unique ID, right? So the Google implementation was never made available. So last February, I took time to implement it myself and see what I could come up with. So I have the link to the patch set in the references at the end of these slides. So one change that is needed in addition to expose additional fields to the struct RSEC ABI that's exposed to user space. So how I plan to extend this is not the topic of this talk, but this has been discussed with the glibc maintainers and they seem to be happy with it. So, but yeah, we focus here on the modifications to the scheduler that are needed. So I extended the scheduler to continuously track, so ongoing, track the number of threads that run concurrently on behalf of each memory space, MM, short for memory space. Usually people call that a process, but I mean, there's clone VM. So using clone, you could create things that kind of share a MM. I mean, there are weird cases. So really it's a memory space. So when the scheduler switches to a new thread, to a thread, not necessarily new, not just created. That thread is assigned a vCPU ID, which is guaranteed to be unused by any other thread from the same memory space until the thread is scheduled out. So you have exclusive access to your per CPU data. That's what it means. This can be done with a per memory space bitmap, which I call a vCPU mask. And its max number of bit is limited, is bounded by the number of possible CPUs on the system. The updates are atomic operations, atomic bit test and set, and atomic bit clear. So we have to be careful about adding atomic operations on the scheduler context switch fastpath because it's frowned upon by the scheduler maintainers for very good reasons. So here's a benchmark with Hackbench that shows significant overhead that I would say, simplistic implementation brings. So without any further optimization, running the Hackbench workload, if we look in a per thread mode, we can see we have 46% overhead, which is fairly noticeable on the Hackbench benchmark. So it's not visible for the per process Hackbench, neither is it for 10 processes each per thread. So my guess there is that the context switch overhead, that includes a switch switching between memory space between threads belonging to two different processes, is much more expensive than the atomic operation. So maybe that's why we don't see it. But maybe I just did not find the right workload to get it to show up. Because the other cases, I mean, the difference is not significant. For perf bench, I ran again. So on all the perf bench workload I've run so far, I could not figure a significant overhead difference with the, again, simplistic implementation, where I basically add the atomic bit test and set and the atomic bit clear to the scheduler fastpath. But again, I might just not have found the right workload. So that's an open call to especially Google, who use that in the field or on their workload to provide benchmarks of their TC-Madoc adapted to this patch set. So a few words about the approach on opt-in or always on for this vCPU ID field. So considering the impact on the scheduler performance, the approach that Google have taken in their internal implementation, as far as I know, is to make the vCPU ID allocation opt-in per process. But given that my goal is to have glibc use that for its memory allocator all the time, I mean, being opt-in maybe will help, but for now, but as soon as glibc will be updated, everyone's going to opt in, every process, almost. So I don't see it as a good approach to tackle performance overhead issues. So what I want to rather do is to make sure that the performance impact is really as minimal as possible. So here's what I did. I identified specific scenarios which are extremely common, and I did performance improvement on them. The first one, it's the single-threaded memory space. So you have a process with a single thread. Many processes in the system are single-threaded. Well, the solution there, well, put it simply, is to just return 0. I mean, you have a single thread. It can use bucket 0, right? On NUMA, it's a bit different because, I mean, yeah, that can be a constant for each NUMA node. Because I'll talk more about NUMA later, but I want NUMA to make sure that every CPU ID that is returned, or virtual CPU ID that is returned, its association with the current NUMA node stays invariant for the lifetime of the process, just as if it was a real CPU. Unless there's a NUMA topology change, but that almost never happens. So, and if it happens, well, user space should deal with it and update whatever they have allocated, or yeah, or be slower. Yeah. Scheduling between threads from the same MM. Okay, So that's a workload where you have one process with many threads, and you basically schedule around between threads that belong to this same process. So for this use case, which is quite common, just handing over. So you allocate a vCPU ID, let's say 5. Okay, so I'm this thread, I have vCPU ID 5. I'm context switching out this thread, and I notice that I'm going to a thread that belongs to the same MM. I just can take this value 5 without putting it back into the bitmap, and I just give it to the next thread. It belongs to it now. So that's easy, and that's fast. So, and those two are trivial to do. So those come without question. I mean, there's no complexity associated. It's the last one that's a bit more complex. So I noticed that for workloads which are kind of in betweens, let's say you have a pair of processes, 2 processes. Each are multi-threaded, heavily multi-threaded. So you have a mix of the scheduler switching between threads within the same process, but also scheduling between threads of those different processes. So there, none of the 2 first optimization change anything. You basically need to relatively, well, whenever you switch between threads belonging to different processes, you need to take the extra atomics. Again, it might not be an issue if we assume that the switch MM, switching between memory space overhead, is large enough compared to the atomics, but I did not want to take any chance, so I created a mechanism. So it's a per run queue cache of pairs of vCPU ID MMs. So I keep, I don't remember, maybe 8 or 16 entries, maybe 8, in an array within each run queue, and it's a cache. And then basically, whenever I run out of space, I just kick out the oldest one. So that takes care of the case where you have multi-process, multi-threaded. So I confirmed my approach with, so within my patch set, I added SCEDStats instrumentation of all the various paths, so all the lookups of the cache, all the eviction, the discard, the case of transfer between threads, which is the other optimization I discussed for the single process multi-threaded case. The single-threaded vCPU ID, so that's the passing over between 2 threads belonging to the same process. Then the vCPU ID allocation, the bit set, so that's the expensive one. And then on release MM and migration, the bit clear that's required. So I instrumented all this with the SCEDStats, getting counters, and here's the result. With the perf bench, SCED messaging, single instance, multi-process. So you end up with the single-threaded vCPU ID is almost all the time what is hit. I mean, there's other things running in the system, right? So I might have a few applications that are also multi-threaded, but I mean, they're in the noise. But so it hits pretty well. Then, and this is run in a loop. So maybe, I don't know, 10,000 times or something like that. Then for SCED switch, for the the messaging perf bench benchmark, this one is multi-threaded. So as you see, the first optimization almost never hits. The second one, transferring between threads, it's almost all the time. And then a few run queue cache hit. Then we have, so this is 2 instances of multi-threaded perf bench SCED messaging. So this case is really, you have 2 processes, each is multi-threaded, and yeah. So as you can see here, the transfer between threads, it's pretty often. So it looks like the scheduler is pretty often scheduling between threads within the same process. But yet you see around 10% of run queue cache hit. So that optimization is doing some good. Well, I mean, it does not say whether the code implementing the lookup is actually faster than an atomic. That's something that we would have to verify separately. And then for the perf-bench sched pipe, one instance multiprocess. Again, it's the single-threaded vCPU ID that hits exactly all the time. So we don't even have to do the atomics in this case, ever. So for Hackbench, with the, I recall the benchmarks I showed a few slides earlier, where we add a significant overhead with the per thread Hackbench. So with the optimizations in place, the per thread Hackbench, then in this case now the difference is not significant. The overhead is not significant of the feature. Question over there. Do you want Mike?
How many threads does that CPU have?
So okay, it's really far from the perfect machine for taking benchmarks. Okay, because I learned that I was going to give this talk 3 days ago. So it's a 16-core machine, but it has hyper-threading enabled, and I was traveling, so I could not easily disable it. And it's running in a VM, but the VM, so KVM, but it's NUMA as well, but the NUMA topology is replicated in the KVM. So that's what it is.
So so you're executing 32?
Yeah, that would be a logical core visible from user space is 32. Yes.
Right, and you have 10 groups using 40. So are you? How many? You're executing 10 on 64, right?
I would guess so. I mean, I mainly ran Hackbench without specifying any option in this case, other than -T for the per thread. So whatever it, I have not looked again at what it auto check on the system and whether it scales its workload to the number of visible logical cores. I won't go in this because I'd have to look up the documentation again at this point. But I mean, for me, the important thing was to compare, A/B comparison of baseline compared to the workload I'm applying. And certainly I could run that on another machine I have, which is all set up for more precise benchmarking. And maybe some of the cases that are in the noise here could end up not being in the noise, and we could see a difference. But I just did not have the time to set that up in 3 days.
Yeah, I think you'd need to do a sweep across multiple thread counts to see what happens here. And you said you use a bit field, but it's only the maximum of the core count, correct?
Yes.
So what happens if you go over that in a per task thread count?
If you go over what?
The number of CPUs. Say, for instance, I wanted to run 40 threads.
Oh, yeah, that's okay. Okay, what happens is the scheduler is not going to schedule. So you have 32 run queues. You can run at most concurrently 32 threads, never more. So you're limited to 0 to 31. You can never have to allocate vCPU ID 32, right? 31 is the last one, because you allocate 1 per run queue and you have 32 run queue on your system.
So what does that thread get?
What does, sorry?
What is it? So I have more than that scheduled to run. What happens in your code? The struct, like you're handing out 1 per bit field and the bit field's full.
No, so you say you have 40 threads, right. 32 cores, right?
Yes.
Okay, so the scheduler, let's say it may have 2 threads in the first run queue, 1, 2, I don't know. So it has certain number of threads per run queue, but the number, the currently active threads, there's only 1. The currently running,
so
1 per run queue.
So when a thread goes to sleep, you remove the vCPU ID?
I actually put it in the vCPU ID cache in the run queue. I could put it back into the bitmap, but that would cost me an atomic bit clear. So rather than that, I just put it in the vCPU ID cache in the run queue.
And so what does that cache do when the process wakes back up? You look up in the cache for the process by something else?
Oh, so when is it looked up, or?
Yeah, when you retrieve the vCPU ID.
Yes. So the vCPU ID is retrieved from that run queue whenever we have another thread. So on that run, on that CPU, on that run queue, whenever there's another thread belonging to the same MM that want to be context switched in. So rather than immediately trying to go and allocate a bit from the bitmap, it's going to check, is there an entry available in the cache? If yes, I just take it. It's mine.
Okay. Don't you have to lock the cache too then?
No, I'm in the scheduler. So there's already the run queue lock taken.
So what does it matter if you're setting a bit field or taking one from the cache? What's the difference?
What, sorry?
What does it matter if you're setting a bit in the bit field because it's already protected versus taking one from the cache?
No, the bit field is in the struct MM, which is shared across all cores and all run queues. So for the bit field, you need the atomic because it's shared between cores, but the run queue is per core and thus already protected by the run queue lock.
I see. So the vCPU ID is just a single vCPU ID recorded?
Sorry?
The vCPU ID is just one recorded for that particular run queue?
Yeah, I mean, it happened to take one, so it has it. So let's keep it around a bit until, let's say, okay, the cache gets, let's say, overwritten. And then at this point, okay, we need to clear it, right?
Okay, thank you.
Welcome. Good questions, by the way. More benchmark from perf bench. So again, it did not show any significant overhead before with the simplistic implementation. It still does not show any significant overhead with this implementation with the optimizations in place. So for more benchmarks, I would kindly ask Google to share benchmarks covering execution of their workload with and without the vCPU ID patch. And I might even apply a patch on top of my code or modify my code to make the optimizations that I do configurable. So maybe that they can easily disable the optimizations and do the testing with each, or especially with and without the last one, which is more complex, the per run queue vCPU ID cache. Because I mean, if it does not show any significant performance gain, I mean, let's rip it apart. I mean, it's neat, but yeah, it needs to serve a purpose. I also want to see what are the performance benefits for tcmalloc. They have the code in tcmalloc to wire up their internal vCPU ID code. So they could change it to try it out with my patch set, and I'd like to see how it behaves. Yeah. Okay. So I already talked about that. So NUMA now, and let's see how I'm doing for time. Wow.
About 15 minutes.
Yeah. I'm doing fine. NUMA. NUMA is an interesting beast. My design assumption for NUMA is that it should really be only an optimization which works as is, although less efficiently, without any code change in user space when user space is not NUMA aware. Compared to what I've seen from the comment in the header from tcmalloc, where I kind of think that if they want to deal with NUMA in the way they expose it, they kind of need to change the code in order to really take into account that, oh, it's NUMA or it's not NUMA. So the way I did it, I pushed a bit of the complexity at the kernel level to make it very simple to use in user space. So the guarantee that is needed here, in my opinion, is to be similar to what a real CPU ID provides with respect to its NUMA topology. So that the mapping between a CPU number and its NUMA node ID stays invariant unless there's a NUMA topology change. So in this case, so whenever you get, let's say, a CPU number, you look, oh, it's NUMA node 2. So you can allocate from NUMA node 2, and then whenever you index your per CPU data structures by CPU number, you stay on NUMA node 2 whenever you do the access. So the ones that do the access do it from the same NUMA node as the ones that reserved the memory, allocated the memory. So the guarantees I want to provide for the vCPU ID is that for the lifetime of a process, the mapping between vCPU ID and NUMA node ID stay invariant unless there is a NUMA topology change in the kernel. So it's pretty much the same thing I want to provide as a guarantee. So that vCPU ID should stay associated with that same NUMA node. So, so the use case there is to allow allocating NUMA local memory on first use of a vCPU ID. So the first time a thread within a process observes a vCPU ID number, should be able to ask the kernel to allocate NUMA local memory. And then all the following accesses from this vCPU ID should be NUMA local. So how I do that is to expose an additional node ID field in struct_rsec in addition to the vCPU ID. And then I use a rsec critical section to load both fields atomically with respect to migration, so that we are guaranteed that we indeed have a pair that will be invariant every time both are read. So, and actually reading both is only needed when you do the original allocation that needs to be on this specific NUMA node number. In the other cases, when you want to do the accesses, you want to be statistically on the right NUMA node number, but if it turns out that you might not be or whatever, it's not the end of the world. Of course, if you do that from within a rsec critical section, we handle the abort for you and everything, so that's going to be fine. But I mean, it can also be used for situations where you're not using it from a rsec critical section. Okay, internally, what I did is to implement that by adding the following bitmaps to each Each bitmap, their max number of bits is still a number of possible CPUs. So there's one bitmap per NUMA node, which I call the vCPU ID allocation bitmap. And one more, which is a bitmap that keeps track of overall what has been allocated in terms of IDs. So overall what we have one bitmap that we had before, which is not for NUMA. It's in all the cases, we have this bitmap that keeps track of what are the IDs that are currently in use in the process. This bitmap is still valid, and this is really the one with the test and set and everything that defines, okay, this ID is reserved and given to a thread at the moment. These other bitmaps allow us to figure out whenever we want to, so whenever we need to allocate an ID, we will want to reuse IDs that have been provided for the NUMA node on which we currently are. So it keeps track of all the vCPU IDs that have been given in the past for each NUMA node. And then the last one, the allocation bitmap, it just keeps track of, in the past history of this process, which of the IDs were at all allocated. So with all this information, what I can do, so I actually extended the find first operations that we have on CPU masks to add two new ones. So CPU mask find 0 and 0, and CPU mask find 1 and 0. And this allows me to scan 2-bit masks in parallel. So, and basically I can look at the current NUMA node bit mask and the allocation and the currently used mask. And I need to find the first one, which has been previously allocated for my NUMA node, but is not currently in use. And then when I find it, I can do the test and set on the used mask. If I get it, perfect, then I use it. If I cannot find any, then I need to allocate a new one. Then I use the last mask, the previously allocated mask. I scan it to see what is the first one that was not previously allocated and is not in use, which then I can go and allocate and use. So that's how it works. Yeah, so the updates to those NUMA-specific bitmaps, they only need to be done the first time a vCPU ID is allocated for a memory space. All the fast paths are lookups. They're just scanning bitmaps, reading word by word, trying to find the first pair that we are looking for. So there are some open questions, some of which I've had the chance to discuss over IRC today with Peter Zistra. Because he was not sure he could make it at this time of the day. So one of the questions I had was, should the scheduler use per NUMA node vCPU ID allocation bitmap to take it into account when taking migration decisions? So it's based on discussions with the Google guys, where it turns out they did not. So they have some code to do NUMA-aware vCPU ID, but they don't turn it on, and they claim that they have better benchmarks when they don't enable it. And I kind of wonder whether it's caused by scheduler decision about where it migrates or places new threads when they are created, and whether there would be a gain to have to use knowledge about where there are vCPU IDs available to spawn those threads, rather than just spawn them, let's say, on a NUMA node where there's been no data structures allocated on that NUMA node yet. So, I mean, those are open questions.
Can I just quickly interject, Mathieu? So for the per NUMA, like using the vCPU ID when determining whether to migrate a task between NUMA nodes, it seems useful, but the whole mechanism for determining where to migrate pages between NUMA nodes and then where to put tasks to have better locality, I feel like it's just kind of a constant, back and forth game that the CPU scheduler plays with the memory sched, the memsched logic. So I almost wonder if we want to like take a step back and think about a more general approach. Like, could this plug into, like the watermark logic where we figure out which pages to demote to like slower NUMA node, slower memory tiers and stuff like that, instead of having it kind of be like another like variable and kind of the decision for the game that they play, if that makes sense.
Sorry, yeah, possibly, but yeah. I don't know, okay. Should be looked into. Another question I had mainly for Peter was so currently what I'm doing is I extend the size of struct_mm to add those bit map at the end. And the size does not seem to be such an issue, at least for Peter. But the alternative would be to add a pointer to struct_mm to point to my data structure, but then you get an extra pointer dereference on the scheduler fastpath. So, I mean, Peter is more in the opinion of extending the struct_mm size. And then open idea, maybe that the cache idea, the per run queue cache that I did, could be reused to cache the MM user references as well. So, the active MM concept in the kernel, where there's ref counting, and so there's been quite a bit of discussion on how to improve things there performance-wise in the community in the recent years. And maybe that's one approach to keep it in mind, to just kind of keep that reference in a cache in the run queue until either it gets kicked out or gets reused. Currently, the kernel does something relatively similar to that. Whenever the scheduler schedules a kernel thread, it kind of keeps an active MM reference until, just because a common case is then to schedule back to a thread belonging to the same MM. So it just never releases that reference. But here what I do is I kind of generalize that to be able to kind of handle keeping more than one So it's a cache of a few entries that you can keep references around. So I don't know. Maybe it could help. Maybe not. So I would like to make this available for shared memory as well per container. I'm going to discuss that at the Containers Micro Conference, so you're welcome to come there. Here are the references, and I think we have a bit of time for discussion. Yeah, 4 minutes. Yeah.
Just double checking whether I did understand something. If, let's say, the CPU ID 2 has been on node 5, does that mean that the CPU ID 2 will always be on node 5?
The only exception is on PowerPC because they support dynamic reconfiguration of the NUMA topology. That's the only exception I know. So it can change. So user space should not abort, ideally, should, yeah. But yeah, other than that, it's going to stay the same.
Regarding PowerPC, there is no reconfiguration of the NUMA topology. That cannot happen.
Well, it's Outplug that does it. Right?
Yes, exactly. Yeah. But in that case, this is better to keep the CPU ID attached to the node, even if that node is no more existing.
Ideally, yes, but
yeah, because from user space application, we have cases where we are doing migration that's changed the NUMA topology, but the kernel cannot reflect the topology the hypervisor is exposing, and we have to. We can do a hot plug of CPUs to realign, but for the user space application, they don't like to see the CPU IDs migrating from one node to another one. That's something they don't want to see. And I think that's better to keep that wired in some way.
Yeah, but I mean, I expose the current node ID and I expose this vCPU ID number. I mean, what happens to the mapping between them is a result of, I mean, I have a limit as well. I have a limit of the number of possible cores. And because of that limit, in the rare cases where there would be a topology change, I need to go and do stealing of the CPU ID from one node to the other.
I agree. That's the problem. Yeah, I agree. That may happen. That's, yeah. But I think we will have to extend the number of CPU IDs inside the kernel to get higher numbers. But the bitmap will be larger.
Yeah, but I mean, so far I think PowerPC is the only architecture that has this weirdness. I'm not aware of any other.
But I think you can get it also with KeyVM, migrating VM from one node to another one.
Maybe. I mean, this is definitely something to look into, but
yeah. That's a mess. I agree.
Other questions?
Don't have any online questions, so I think maybe that's it.
Yeah. Thank you, everyone. Have a great evening, and thanks for listening to my talk.